There's a galaxy so vast the Milky Way could vanish inside it, not once but dozens of times, and still be swallowed by its light. Its name is IC 11-1, a cosmic city of stars so big it feels like a mistake the universe shouldn't be able to make. So what kind of violent, danger-filled history could build a monster like this, and what does it reveal about what's really waiting in the dark between galaxies? Somewhere in Virgo, a pale smear of light marks a throne where gravity has been ruling for billions of years, and when you stare at it long enough, the universe stops feeling spacious and starts feeling crowded. IC 11-1 doesn't announce itself with spiral arms or bright fireworks. It hides in softness, in edges that refuse to stay still. Its outer light is so faint that where it ends becomes a choice, not a line, and that choice changes everything. Because if a galaxy can blur into its surroundings until the sky itself looks inhabited, then our maps of the cosmos are fragile. Tonight, we follow that fragility like a thread, through deep images, careful subtraction, and the quiet mathematics of starlight. We will ask a single question with unforgiving patience. How did IC 11-1 become so enormous, and what does that enormity imply? Not as a headline, but as a physical record, written by collisions, stripped stars, and time's indifferent accumulation. To understand it, we have to learn what astronomers mean by size, when the boundary dissolves into intracluster glow. We have to treat this galaxy like a case file, half evidence, half inference, assembled from photons that arrive already exhausted. We will step into Abell 2029, a gravitational metropolis where hundreds of galaxies move like traffic around an unseen centre. There, hot gas burns in X-rays, velocities run high, and the most important mass refuses to shine at all. In that darkness, the story stops being only about a single galaxy and becomes about the architecture beneath galaxies. We will descend toward the core, where a black hole's influence is measured not by visibility, but by what it compels. Then we will pull back until familiar distances break, and the solar system becomes less a neighbourhood than a notation. Along the way, we'll keep one human anchor, worlds around other stars, because scale is terrifying only when it touches possibility. And at the edge of our instruments, we will confront the most unsettling twist. The record itself may be conditional, because biggest, known, and even galaxy are not simple words out here, they are agreements under pressure. If IC 11-1 is real in the way we think, it is a monument to gravity plus dark matter plus time, nothing more, and that is why it feels like an omen, not of malice, but of honesty, as the cosmos reveals what it can build without us. This journey is a slow widening of the frame, until the question is no longer how large IC 11-1 is, but what else we've missed. So we begin where all cosmic horror begins, with measurement, with doubt, and with a glow that should not be so hard to see. Before we begin, let us know in the comments below where in the world you're watching from, and what time it is there. Now settle in for a journey. We'll start by breaking intuition with scale, then investigate how IC 11-1 is measured, and why its edge may be a moving target. From there, we trace the violent growth of galaxies, the pull of black holes, and the invisible scaffolding that makes giants possible. Imagine the Milky Way as a familiar disk of stars, 100,000 light-years wide, with spiral arms you can sketch from memory. Now imagine a single galaxy stretching up to 6 million light-years across, so large it breaks intuition and resists mental pictures. If the Milky Way were a coin on a tabletop, IC 11-1 would be a stadium-sized circle of faint light, barely visible at the edges. If you lined Milky Way's edge to edge, you could fit dozens across IC 11-1's diameter, like tiles spanning a floor. Not dozens of stars, not dozens of solar systems, but dozens of entire galaxies, each with its own history, its own dark matter halo, and its own billions of suns. A light-year sounds like time, but it is distance measured by light's speed, and that difference matters for every claim we make. Light travels about 300,000 kilometers each second, circling Earth more than 7 times in one heartbeat. In 1 year, it covers nearly 10 trillion kilometers, and that is 1 light-year, a ruler built from physics. Multiply that by millions, and the numbers stop behaving like everyday reality, because the mind was not built for cosmic units. This documentary begins with that failure of scale, because it is the point, not a gimmick. IC1101 is not just big in a record book sense, like a tallest building on a list. It is big in a way that demands a story about violence, gravity, and deep time, because nothing grows to that size gently. IC1101 sits more than 1 billion light-years away, in the direction of the constellation Virgo. It is the central dominant galaxy, a CD galaxy, in the galaxy cluster Abell 2029, and that address explains its power. It lives where the universe gathers its mass, where galaxies crowd together like buildings in a dense city, and where the sky is never truly empty. Galaxy clusters are the universe's cities, built by gravity over billions of years, and they are among the largest structures that remain gravitationally bound. They contain hundreds to thousands of galaxies, plus vast reservoirs of hot gas that can outweigh the stars themselves. Most of their mass is invisible, held in dark matter halos that shape everything we see, because gravity responds to mass whether it shines or not. In these crowded environments, the biggest monsters tend to live downtown, where the gravitational traffic never stops and the merger rate stays high. Galaxies fall inward along filaments of the cosmic web, and the cluster core acts like a drain. Over time, the central galaxy becomes a collector, sometimes a predator, growing by absorbing what the cluster delivers. Abell 2029 is one of those cities, and IC1101 is its central landmark, a luminous anchor in a sea of faint companions. It is not a spiral like the Milky Way, with crisp arms and a bright disk where new stars form. It is an enormous elliptical system, with a bright core and a huge diffuse envelope, dominated by older, redder stars that formed long ago. In a still image, an elliptical galaxy can look serene, like a smooth lantern against black space, but the calm is deceptive. Ellipticals are often the aftermath of collisions, when spirals smash together and their ordered disks are scrambled into a rounded swarm. The orbits of billions of stars become randomized, and the galaxy's shape turns into a kind of fossil record of past impacts. IC1101's outer light is so faint that its true edge becomes a question, not a line, and that uncertainty is part of the story. The halo fades gradually, photon by photon, until it competes with the background glow of the universe itself. At that point, size depends on how deep you look, how carefully you subtract stray light, and how you define what counts as belonging. That uncertainty is not a technical footnote. It is part of the mystery, because the boundary is where history accumulates. When scientists say IC1101 may reach 6 million light-years, they are describing an envelope that dissolves into darkness rather than stopping. The galaxy's boundary depends on how deep you look, what you count as belonging, and how you separate galaxy from cluster, which is harder than it sounds. Measuring size becomes a scientific thriller because the stakes are physical, not merely semantic, and the data are unforgiving. Astronomers fit brightness profiles to the galaxy's light, looking for where the curve changes slope as the halo takes over. They compare that glow to the intra-cluster background, because the cluster itself is not black. It is filled with scattered starlight. If the outer envelope is truly part of the galaxy, then IC1101 is a monument to mergers, built by repeated cannibalism in the cluster core. If much of that light belongs to the cluster itself, then the cluster is stripping galaxies and smearing them into intra-cluster glow. Either way, the environment is extreme, and the history is written in debris like smoke that never fully disperses. In the center, stars crowd together in an old, massive population, and the density rises toward a core that can outshine entire smaller galaxies. Farther out, the starlight thins into a ghostly halo that can swallow smaller galaxies before you even notice they are falling. The galaxy looks calm in a still image, but its scale implies a past full of collisions, because growth at this level requires repeated capture. In clusters, galaxies do not live alone, and the central one grows by taking what falls in, sometimes through dramatic mergers and sometimes through slow stripping. A smaller galaxy can be torn apart by tidal forces, its stars stretched into streams and shells that wrap around the giant. Over time, those streams blur into a smooth envelope, turning violence into a faint, almost elegant glow. This is where awe turns into unease, because the size hints at forces we cannot touch, and at mass we cannot see. Dark matter is the scaffolding that holds clusters together, and it may be the reason IC1101 could grow so large. The visible stars are only a tracer, outlining a gravitational structure that is mostly unseen, like frost revealing the shape of an invisible window pane. The monster we can photograph may be only the glow on the surface of something deeper, a dark halo extending far beyond the starlight. In simulations of structure formation, dark matter collapses first, forming wells that ordinary matter falls into later. If IC1101 sits in an unusually massive well, then its growth becomes less surprising, even if it remains staggering. Our maps of the universe are built from light, and light is limited, not only by distance but by contrast. The farther we look, the more the universe hides behind distance, dust, and faintness, and the more every measurement depends on careful calibration. IC1101 challenges us because it sits at the edge of what surveys can measure cleanly, where the halo is barely brighter than the background. Its halo is a test of instruments, methods, and patience, because faint light is where errors masquerade as discoveries. Astronomers must account for the telescope's scattered light, for the glow of Earth's atmosphere in ground-based images, and for the combined haze of unresolved galaxies. When you're chasing the edge of a giant, the edge of your detector becomes part of the story. Modern astronomy makes this challenge possible, and it also makes it unsettling, because the sky has become a dataset as much as a view. NASA missions and ground-based observatories have turned the sky into numbers, not just pictures, and those numbers can be pushed to extremes. Hubble-class observations can resolve structure in distant galaxies and measure their profiles into faint outskirts, while wide-field surveys can trace clusters across enormous angles of sky. Those surveys do more than count galaxies, because clusters bend light and trap heat, leaving multiple signatures. The cluster's hot gas shines in X-rays, revealing deep gravitational wells, and that glow can outline the cluster's shape like a thermal map. Lensing and dynamics trace dark matter, showing where mass hides even when light fades, and reminding us that the brightest object is not always the heaviest component. Yet even with that technology, IC1101 refuses to be simple, because nature does not label its parts for us. Its brightness profile does not end like a neat object against black space, the way a planet's edge cuts cleanly against the sky. It blends into the intracluster light, the diffuse glow from stars no longer bound to any single galaxy, and that blending is a clue to constant disruption. The more carefully we measure, the more we realize the universe does not respect our categories, because galaxy and cluster overlap in the core. A CD galaxy is almost defined by that overlap, with an envelope that feels like a bridge between one object and its environment. When boundaries blur, we are forced to ask whether our definitions are describing reality or just making it easier to talk. That is why this opening chapter begins with a comparison that feels physically impossible, because it resets the scale of everything that follows. A galaxy millions of light years wide is not just a bigger version of home, scaled up like a model. It is a different kind of structure, assembled by a different kind of history, and shaped by the relentless statistics of crowded space. It forces a question that will drive the rest of this documentary, and it is a question with several sharp edges. How did IC1101 become the largest known galaxy in the observable universe? And what does largest even mean when the outskirts are so faint? What sequence of mergers, cluster dynamics, and dark matter architecture built something this vast? And what evidence should we expect to find if that story is true? And if a galaxy like this can exist, what else exists beyond our current catalogues, beyond the thresholds of our surveys, beyond the comfortable range of our definitions? Are there other giants whose halos are simply too diffuse to stand out against the cosmic background? Or are we looking at a rare outcome, a statistical extreme that teaches us how the universe behaves at its limits? The fear is not that IC1101 will reach us, because it is far beyond any practical threat, separated by distance and by cosmic expansion. The fear is what it implies about scale and about limits, because scale changes what feels possible. If galaxies can grow into million light-year envelopes, then the universe has room for structures we have barely begun to name, and our sense of distance becomes a fragile local habit. It suggests that our sense of travel and control is a local illusion, built inside a small, warm neighbourhood of space. Even within our own galaxy, distances are so large that the nearest stars are years away at light speed. Against IC1101, even the Milky Way starts to feel like a small town, and the cluster core becomes a continent. Consider our own emissaries, Voyager and Voyager 2, still moving outward after decades, carrying gold records and the quiet optimism of the 1970s. They are among the farthest human-made objects, crossing the outer boundary of the sun's influence into interstellar space. Their speed is heroic by human standards and irrelevant by galactic ones, because the gulf between stars is built on light years, not kilometers. Against ICL 1101's diameter, their journey is a rounding error, a scratch on the scale bar of a cosmic map. If you could place the Voyagers on a diagram of Abell 2029, they would disappear into the thickness of the line. That contrast is not meant to humiliate us, but to clarify the arena we're trying to understand. That contrast is the documentary's emotional engine, because it holds wonder and limitation in the same frame. We are a species that measures, maps, and sends machines into the dark, and we do it with stubborn creativity. We are also a species trapped by physics, by finite lifetimes, and by the speed of light, and the universe does not bend those rules for curiosity. IC 1101 sits in the distance like a reminder that the universe is not built for us, and yet it is still legible. Still, we can learn its story, because gravity leaves clues, and those clues persist for billions of years. The shape of the halo, the distribution of stars, and the motions of galaxies in Abell 2029 all encode the past, like a crime scene preserved in slow motion. The cluster's hot gas shines in X-rays, revealing deep gravitational wells, and it also reveals the violence of the environment. The gas is heated to tens of millions of degrees, not by fire, but by gravity converting infall into heat. When galaxies plunge through it, they can be stripped of their own gas, shutting down star formation and leaving behind older stellar populations. IC 1101 becomes a case study in cosmic growth at the highest extreme, where the usual rules are pushed into their most dramatic forms. It is a laboratory for the idea that the biggest galaxies are made, not born, assembled from many ancestors. It tests models of hierarchical structure formation, where small objects merge into larger ones over time, and where the present is a layered archive of past accretion. It also tests the boundary between a galaxy and its environment, a boundary that may be more psychological than physical, because our language prefers clean edges. When we say galaxy, we imagine a self-contained island, but cluster cores are more like archipelagos. Stars can be bound loosely, traded between systems or set adrift, and the light we see becomes a shared atmosphere. There is another tension beneath the numbers, and it is about what we can ever reach, even in principle. 1 billion light years is not just far, it is time, because the light we see began its journey long ago. The light we see left IC 1101 long before complex life on Earth had its current form, meaning our observation is a kind of archaeology. We are studying a distant past, and we cannot send anything there without waiting longer than civilizations last, even if we could travel near light speed. That constraint turns astronomy into a science of inference, where we read patterns and test models rather than visiting. It also makes every image feel like a message from a time we can never touch. So the central question is not only how IC 1101 formed, but what its existence reveals about the cosmos that formed it. Does it point to unusually efficient merging in dense cluster cores, where orbits decay and galaxies sink inward? Does it reveal a particularly massive dark matter halo that gathered more material than expected, deepening the well that everything falls into? Or does it expose a measurement problem, where our definitions of size fail in the faint outskirts, and where galaxy becomes inseparable from cluster light? Each answer carries a different implication about the cosmos, and each one changes what we think the universe is willing to build. If IC 1101 is truly that large, then extreme growth is possible under the right conditions, and our simulations must reproduce it without special pleading. If its halo is partly intracluster light, then clusters are even more dynamic and destructive than we imagine, constantly shredding their members and recycling their stars. If our methods are uncertain, then the universe may be full of giants we have not recognized, hidden not by distance but by faintness. In that case, the frontier is not only farther away, it is dimmer, and it demands better ways of seeing. This chapter is the doorway into that investigation, and the doorway is deliberately unsettling, because it asks us to doubt our instincts. We begin with a galaxy that seems too large to be real, then we place it in its city of galaxies, where scale becomes plausible. We admit what we know, and we underline what we do not know, because uncertainty is where the science lives. We treat size as evidence, not trivia, and we treat the faint edge as a clue, not an inconvenience. Next, we follow the clues that size leaves behind, from the crowded core to the fading edge, where the last photons struggle to stand out. We move from simple comparison to physical mechanism, from shock to explanation, and we keep asking what the environment is doing to the object at its centre. We ask what kind of cosmic weather builds a central dominant galaxy, and what it costs the surrounding galaxies that share the same gravitational streets. We ask what gets swallowed, what gets stripped, and what gets left floating between, contributing to that ghostly intra-cluster glow. In a cluster like Abell 2029, even survival has a price, and the price is written in missing gas and scattered stars. IC 1101 is a monster made of starlight and dark matter, shaped by time and collision, and polished by the mathematics of gravity. It is also a signpost, pointing toward the larger scales the universe can assemble without flying apart, and it forces the final hook that hangs over everything that follows, a question that turns curiosity into momentum. If this is what we have found, what have we not yet seen, and what is waiting just below the thresholds of our instruments? From here, we go deeper into Abell 2029, into the physics of clusters, and into the merger history that can inflate a galaxy beyond intuition. We leave the comfort of the Milky Way's familiar shape and step into a city where gravity never sleeps. IC 1101 is not found like a landmark. It is found like a suspect, half seen, half inferred, hiding in noise that looks at first glance like empty sky. At 1 billion light-years, the galaxy is not a place you could point to with certainty. It is a delayed signal arriving now, carrying a timestamp embedded in every photon. Distance in astronomy is also time, and that is not a metaphor. The light left IC 1101 long before Earth's recent history finished unfolding, before our modern instruments even existed. That time delay matters because the universe expands while the light travels, and expansion is not passive scenery. The stretching of space changes the light itself, altering wavelengths in a way that can be measured precisely. The first clue is redshift. Spectral lines, sharp fingerprints from elements like hydrogen, calcium, and magnesium, slide toward longer wavelengths as space stretches between source and observer. Redshift is not just a colour shift, and it is not a trick of motion through space alone. It is a measurement of recession tied to cosmic expansion, a quantitative link between the spectrum and the scale of the universe. Measure the shift, estimate the velocity, and connect it to the Hubble relation. That is the opening move, because the slope of that relation turns wavelength displacement into a rough distance. The method sounds clean, but the real sky is messy. At cluster distances, velocity is not the whole story, because gravity adds peculiar motions that ride on top of expansion. A galaxy can be pulled inward by the cluster's mass, while the universe carries it outward overall. Those competing motions complicate the inference, and they widen the error bars in any single redshift-based distance. So astronomers build a distance ladder, not out of tradition, but out of necessity. They cross-check methods that work at different ranges, stitching the scale together from overlapping rungs. Nearby, parallax anchors the scale with geometry. As Earth orbits the Sun, a star's apparent position shifts against distant background points, and that tiny angle, measured in arcseconds, sets a baseline for everything else. Farther out, standard candles and standard rulers take over, and they do it with calibrated assumptions. Cepheid variables pulse with period luminosity regularity, Type IR supernovae explode with repeatable peak brightness, and baryon acoustic features provide statistical yardsticks. For Abell 2029, redshift becomes the practical ruler, because the cluster sits far beyond where parallax or individual Cepheids can help. The cluster's spectrum places it in the deep background of our sky, where distance is inferred rather than directly measured. That placement turns IC 1101 into a snapshot from earlier cosmic time. We are not seeing it as it is, because now at the galaxy and now on Earth are separated by the travel time of light. We are seeing it as it was, when the universe was younger and the cluster's core was still evolving. The image is a historical document, and the telescope is the archive reader. In visuals, the scene is almost cruelly understated. A dark field, a scattered spray of faint galaxies, and then a central glow that seems ordinary until you realize how far away it is. Now the case file shifts from where it is to what it is. Classification becomes the next filter, because naming the object is a way of narrowing the physics. ICR 1101 is tagged as a CD galaxy, and the letters carry a history of observational shorthand. The label means central, dominant, and wrapped in an extended envelope that can blend into the cluster's own diffuse light. CD galaxies sit at cluster centers because the potential well is deepest there, and the environment feeds them. Over billions of years, satellites spiral inward, interactions heat stellar orbits, and the central object grows by accretion and mergers. Astronomers confirm the setting by mapping member galaxies across the field. They look for a shared redshift and a shared motion pattern because a true cluster is a gravitational family, not a chance alignment. They also map the cluster's hot gas in X-rays, where the physics is stark and unforgiving. That glow traces the gravitational basin that holds everything, because gas at tens of millions of degrees radiates as it is confined by the cluster's mass. In Abell 2029, the X-ray halo is strong, smooth, and centrally concentrated. It signals a massive, relatively relaxed cluster with a dense core, the kind of environment where a central dominant can become exceptionally extended. A dense core is where giant ellipticals thrive, and it is also where boundaries between galaxy and cluster blur. The central region becomes less like a single object, and more like a layered structure of stars, gas, and dark matter. The next problem is deceptively simple, and it sounds like it should be solved with a ruler. How do you measure the size of something that fades gradually, without a hard edge, and without a clear border? Galaxies do not have edges like planets. Their light declines with radius until it merges with background, and the outermost stars are so sparse that the galaxy becomes a statistical excess rather than a visible outline. So size depends on definition, and definition depends on what the data can support. Astronomers choose metrics that can be measured consistently across surveys, because consistency is what turns a single image into a comparable measurement. One common metric is effective radius, the radius enclosing half the total measured light. It is a practical compromise, because half light can be estimated even when the outskirts are uncertain. Effective radius is useful because it is stable under noise, and it tends to be reproducible between instruments. It is also incomplete for monsters with huge halos, because half the light can sit relatively close to the core, while the envelope stretches far outward. Another metric is an isophotal radius, the radius where surface brightness falls to a chosen threshold. In other words, it is where the galaxy becomes as faint as the survey is willing to call real. That threshold is not a law of nature. It is a compromise between detectability and comparability, and it is shaped by sky brightness, exposure time, and the discipline of the reduction pipeline. For IC 1101, the threshold choice changes the answer dramatically, and that is the point. The outskirts are the whole argument, because the outer envelope is where the galaxy's extremeness either appears or disappears. The halo is faint because the stars are spread thin across a vast volume. Surface brightness drops even when total mass stays enormous, because brightness per unit area is diluted as the envelope expands. Surface brightness is the key enemy at distance, and it punishes extended objects first. Flux dims with distance, and a large object spreads that flux over many pixels, making each pixel only slightly brighter than the background. Cosmology adds another penalty that is easy to underestimate. Surface brightness dims with redshift in a steep, unforgiving way, so the same physical halo becomes dramatically harder to detect as you look farther back in time. That dimming means the outer envelope can vanish into the sky background, and the galaxy can look smaller than it is. The disappearance is not physical but observational, an erasure by noise. So astronomers fight the background with methods that feel almost forensic. They model the sky, subtract scattered light, and correct instrumental signatures, because a tiny offset in the sky level can create a false halo or erase a real one. They also fight their own telescopes because every optical system spreads light into wings that mimic faint halos. Even a perfect mirror produces diffraction patterns, and real optics add microscatter from surfaces and coatings. A bright core can leak photons outward through the point spread function, and that leak can fake an extended envelope. If the PSF is not characterized out to large radii, the galaxy's outskirts become a mirror artifact. To avoid that trap, teams measure the PSF carefully using bright stars in the same field, and they model how much light is redistributed at large radii. They test whether the observed halo follows the PSF shape or diverges from it. Ground-based images add atmospheric glow, and the atmosphere is never truly dark. Airglow, thin clouds, and scattered moonlight raise the floor that halos must rise above, turning the sky into a luminous veil. Space telescopes avoid the atmosphere, but they still face detector systematics, stray light, and calibration drift. A faint gradient across a detector can masquerade as diffuse starlight unless it is corrected with obsessive care. Deep imaging is built from patience, and patience is translated into exposure time. Many exposures are stacked to push the noise down and the halo up, and the stacking must preserve faint structure without smearing it away. Wide-field surveys add another advantage, and it is not just convenience. They capture the cluster background and the galaxy in the same frame, which helps separate local sky variations from genuine diffuse emission. That matters because the cluster is not empty, even when it looks empty. Intracluster light fills the core with diffuse starlight, a ghostly component that can be brighter than the outskirts of any single galaxy. Intracluster light comes from stripped stars, and stripping is routine in a dense environment. Tidal encounters, repeated flybys, and the disruption of satellites scatter stars into the cluster potential, where they orbit without belonging to one galaxy. In a cluster center, the halo of the CD galaxy and the intracluster light overlap, and the overlap is the mystery. The light does not come with labels, and the photons do not announce their origin. If you assign more of that diffuse glow to IC Elena 1, the galaxy becomes enormous, with an envelope that seems to swallow the core of the cluster. If you assign less, it shrinks into a more conventional giant elliptical. This is not a philosophical argument, even if it sounds like one. It is a data reduction argument with physical consequences, because the inferred size feeds into formation models and into comparisons across cosmic time. Astronomers fit brightness profiles to the galaxy, turning an image into a radial function. They test Sursic models and multi-component decompositions, because a single curve rarely captures the complexity of a central dominant. A single smooth profile can hide structure, and it can force unrelated components into one mathematical shape. A second component can represent an extended envelope or intracluster light, and the choice changes the interpretation. Each fit carries assumptions about symmetry, background, and contamination, and each assumption shifts the inferred size. Even the decision to allow ellipticity to vary with radius can change how much light is attributed to the outer regions. They also mask foreground stars and background galaxies, because unmasked sources can inflate the halo artificially. A faint, unresolved background galaxy can look like part of the envelope if it sits in the wrong place. They measure color gradients across radius, and the colors are subtle clues. If the outer light is bluer or redder than the core, it can hint at different stellar populations and different origins. They compare the halo's shape to the cluster potential, looking for alignment and smoothness. A rounder, cluster-aligned envelope suggests shared origin, while a more galaxy-like shape can imply a tighter association with the central object. They look for tidal features in deeper data, because tidal debris is a signature of recent accretion. Streams, shells, and asymmetries imply ongoing stripping, and they turn the halo into a record of dynamical history. But at 1 billion light-years, fine structure is hard to separate from the limits of resolution and depth. The features that would be obvious nearby can be compressed into a few pixels, and the contrast can be swallowed by sky noise, so the case file includes uncertainty ranges, and the ranges are not an embarrassment. IC 11.1's diameter is quoted as a span, not a single number, because the measurement depends on depth, threshold, and modelling choices. The headline numbers can sound absolute, especially when they travel into popular retellings. The scientific version is conditional on definitions and depth, and it is explicit about what the data can and cannot guarantee. Even the star count is an order of magnitude claim, and it is treated that way by professionals. Around 100 trillion stars is plausible, not audited, because the estimate is built from integrated light rather than resolved individuals. Star counts at that distance are not literal counts, and no telescope is tallying points of light one by one. They are inferred from luminosity and mass-to-light ratios, which translate brightness into stellar mass under population assumptions. Mass-to-light ratios depend on stellar populations, and populations carry their own uncertainties. Older, redder stars emit differently than younger, bluer ones, and the initial mass function, how many low-mass stars formed, tilts the conversion. Dust is not the main issue in a giant elliptical, because these systems are typically gas-poor and quiescent. The main issue is how much faint light you can trust when the signal sits near the noise floor. Astronomers cross-check with dynamics, because gravity does not care about surface brightness. Galaxy velocities and gas temperature estimate the cluster mass profile, and the profile constrains what kind of potential could host such an extended envelope. They cross-check with gravitational lensing when possible, because lensing traces mass without caring about starlight. Distortions of background galaxies provide an independent map of the cluster's mass distribution, even when the light is ambiguous. These checks do not draw a sharp edge around IC 1101, and they are not meant to. They constrain the gravitational context that the light must inhabit, narrowing which interpretations are physically plausible. The investigation also depends on historical context, because IC 1101 did not become famous in a single night. It emerges as surveys get deeper and pipelines improve, and as the community learns how to treat low-surface brightness structures responsibly. Older photographic plates could see the bright core, but they struggled with faint outskirts and non-linear response. Modern CCD surveys can chase the envelope into the low-surface brightness regime, where careful calibration makes the difference between discovery and illusion. Space-based imaging refines the central structure, revealing the smooth, pressure-supported character of the inner galaxy. Ground-based wide fields refine the outer profile and background because they can capture the extended environment in one coherent view. NASA missions contribute by mapping wavelengths beyond visible light, and each band adds a different piece of the case. X-ray observatories reveal the cluster's hot atmosphere, while ultraviolet and optical data constrain stellar populations and structural parameters. Infrared surveys help with stellar mass estimates, because infrared light tracks older stars more directly. They reduce sensitivity to recent star formation that ellipticals largely lack, making the mass-to-light conversion less volatile. Large observatories contribute with long integrations, and the trade is always the same. They trade time for depth, and depth for a better boundary, pushing the detectable envelope farther into the dim outskirts. The boundary remains the suspense point, because the biggest objects often have the blurriest borders. Their outskirts are fragile, dynamically loose, and easily confused with the cluster's own diffuse component. Fragile outskirts are easily disturbed by tides and by the constant traffic of satellites near the centre. They are also easily mismeasured, because they sit near the noise floor where small errors in subtraction become large errors in size. That is why IC 1101 feels like a file that never closes, even when the evidence is strong. Each deeper image can extend the halo outward, and each improved subtraction can pull it back inward. The monster grows and shrinks with methodology, and that variability is part of the story. It is a reminder that the universe is not only vast but also faint, and faintness is where measurement becomes interpretation. Yet the core fact survives every revision, and it survives conservative definitions. IC 1101 is extreme, even when the intracluster light is treated cautiously, and the sky subtraction is intentionally strict. Its effective radius is huge for an elliptical, placing it at the far end of known galaxy scaling relations. Its envelope is unusually extended for a galaxy at that redshift, even after accounting for observational dimming, and its location at the centre of Abell 2029 fits the pattern seen across clusters. Cluster centres build central dominance through time, and the central dominant becomes a kind of gravitational ledger of past interactions. So the investigation ends with a controlled unease, the kind that good science produces at the edge of detectability. We can place IC 1101 in space and time, but we cannot draw its true edge with a single definitive line. We can estimate its scale, but we must admit the range, because the outermost light is both physically diffuse and observationally fragile. We can call it the largest known, while knowing the label is provisional and contingent. That provisional label is not weakness, and it is not hedging for its own sake. It is the honest shape of science at the limit of detectability, where the data are real, but the boundaries are negotiable. IC 1101 forces the same question as the opening hook, and it does so with quiet pressure. How can something so vast be assembled without breaking apart, especially in a region where tides and collisions are constant? If measuring it is hard, building it is harder. The next chapter follows the construction story into the cluster core, where gravity, merger history, and the slow churn of stripped stars can inflate a galaxy beyond intuition. From here, we go deeper into Abell 2029, into the physics of clusters, and into the merger history that can turn a central dominant into a structure that feels less like a galaxy and more like a small universe. If measuring IC 1101 is hard, building it is harder. because the universe builds giants by breaking smaller things. The central question stays sharp, and it refuses to soften with distance or time. How did IC 1101 become the largest known galaxy, and what does that reveal about cosmic history? The opening hook still hangs over Abell 2029, like a shadow cast by something too large to name casually. If the Milky Way could fit inside one galaxy, then growth must be violent, repetitive, and statistically inevitable. IC 1101 is not a lucky accident, or a single freak collision that never happened again. It is what gravity does when given crowding, dark matter, and time, then left alone to work. Start at the beginning, before galaxies had names, before stars had stable neighborhoods, before any spiral arm could hold its shape. The early universe was hot, expanding, and almost uniform, yet it carried tiny imperfections that mattered. Those small variations were not artistic noise, but physical seeds, minute differences in density and temperature. Tiny density fluctuations were imprinted in the primordial plasma, then frozen into the cosmic microwave background. In the CMB, they survive as faint mottling across the sky, a baby picture of structure before structure existed. Their contrast is only about 1 part in 100,000, but gravity is patient with small advantages. Those fluctuations were small in amplitude, but they were everywhere, and gravity never ignores a surplus. Regions slightly denser than average slowed their expansion first, because extra mass means extra pull. Over time, those regions stopped expanding with the universe, then began to collapse inward. Dark matter dominated that collapse, because it does not collide with light, and it does not feel pressure. It is effectively invisible, yet it provides most of the mass that shapes cosmic architecture. Where ordinary gas resists compression by heating up, dark matter simply piles up, deepening the gravitational wells. Dark matter formed the first scaffolding, a web of filaments and knots that grew by accretion. In simulations, that web looks like frost spreading across glass, with bright nodes where filaments intersect. Ordinary gas fell into those wells later, heated by infell, then cooled by radiation as atoms shed energy. Where cooling won, gas condensed into the first stars and the first galaxies switched on. The earliest stellar populations were likely massive and short-lived, enriching their surroundings with heavier elements when they exploded. That chemical enrichment mattered, because metals make gas cool more efficiently, accelerating later star formation in growing halos. This is hierarchical structure formation, and it is not a poetic phrase. Small halos form first, because small scales collapse earlier in an expanding universe, especially in the cold dark matter picture. Larger halos form by assembling smaller ones, merging again and again as the cosmic web funnels matter inward. So the universe does not start with giants, and it cannot because early conditions do not allow instant coherence on enormous scales. It starts with fragments, then builds monsters by collision, capture, and slow digestion. Every large galaxy is an archive of smaller ancestors, even when the evidence is smeared into smooth light. There is history in that smoothness, and it is easy to underestimate what it means. A calm-looking halo can be the final state of thousands of disrupted orbits, mixed until individual trails vanish. When we see a giant elliptical with a faint envelope, we're often seeing the end of many stories. In a cluster like Abell 2029, the assembly line runs fast because the environment is dense and the potential is deep. Filaments feed the cluster feeds its core, and the core feeds the central dominant. The environment is a gravitational city, and the downtown traffic never really stops. Visually, the cluster is a swarm of galaxies embedded in a larger invisible mass, with hot gas glowing in X-rays like a blue-white fog. The galaxies are the streetlights, but the dark matter is the road system that forces their paths. At the center, the brightest galaxy sits where the gravitational contours tighten. Galactic cannibalism is not metaphor in this setting, even if the language feels too biological for physics. It is the default outcome when a massive galaxy sits at the bottom of a deep potential well. Satellites pass nearby, lose energy, and sink, because gravity turns orbital motion into heat and disorder. The key mechanism is dynamical friction, and it works like a silent executioner. A satellite galaxy moving through a sea of stars and dark matter creates a gravitational wake, a trailing over density that forms behind it. That wake pulls backward on the satellite, draining orbital energy and angular momentum with every passage. In plain terms, the satellite plows through a crowd, and the crowd's gravity tugs it back. The more massive the satellite, the stronger the wake it raises, and the faster it loses momentum. This is why big intruders do not stay in the outskirts for long. The satellite does not simply orbit forever, even if its initial trajectory looks stable on a short timeline. Its path decays, the orbit shrinks, and pericenter passages become tighter and more destructive. Over time, the satellite spirals inward, not because it wants to fall, but because the background steals its momentum. Dynamical friction is strongest for massive satellites, which makes the process self-accelerating. Big companions sink quickly and deliver their cores deep into the center, sometimes surviving tidal stripping until the last moments. Small companions sink more slowly, but they are easier to shred, and their debris still adds to the halo. This is why clusters grow central dominance, and why those dominants can become absurdly extended. The cluster potential gathers galaxies into the core, then dynamical friction sorts them by mass, pushing the biggest inward first. The central galaxy becomes a collector, and the collector becomes a record of what the cluster has consumed. Now separate mergers into two types, because the outcomes are different, and the signatures they leave are not the same. Major mergers happen when two galaxies of comparable mass collide and coalesce, often within a factor of a few. Minor mergers happen when a large galaxy absorbs a much smaller one, repeating the process many times. Major mergers are the events that erase order, and they do it quickly on galactic timescales. When two spirals merge, their disks are heated and scrambled by tidal forces, and their carefully aligned rotation is broken. Gas clouds collide, star formation can flare, and the final stellar orbits become randomized into a spheroid. A spiral disk is a fragile structure, built from coherent rotation and thin geometry, like a record spinning without wobble. A major merger injects violent relaxation, mixing energies and directions until the disk cannot survive. What gets destroyed is the disk's memory, and what gets built is an elliptical body, pressure-supported and thick. Violent relaxation is not just a dramatic phrase because the gravitational potential changes rapidly during the collision. Stars respond to that changing potential by trading energy in a collective reshuffling, even though they almost never collide directly. The result is a system where random motions dominate over ordered rotation. The remnant is not just rounder, and it is not just older looking. It is also surrounded by an expanded halo, because tidal forces fling stars outward during the encounter. Some stars become loosely bound, some become unbound, and the outer light becomes a faint envelope that can extend far beyond intuition. If you could watch the merger from a distance, you would see long tidal tails, pale, arcing streamers, stretching out like torn fabric. Those tails are not decoration, but mass in transit, carrying stars into the outskirts or into intergalactic space. Over time, the tails fade, yet their stars remain, quietly thickening the halo. Minor mergers are quieter per event, but they are relentless in total, and they are especially effective at building size. Each small satellite is stripped by tides, losing stars into streams and shells that wrap around the host. The central galaxy gains mass, but it gains it mostly in the outskirts, puffing up its radius faster than its core. This is a crucial clue for IC 1101, because the biggest ellipticals often grow inside out. The core can be old and stable, with stars formed early and quickly, while the halo keeps expanding as new debris settles. In that sense, the center is a fossil, while the outskirts are a construction site. Inside-out growth also helps explain why size can increase dramatically, without a proportional increase in central density. When stars are added at large radii, they contribute more to the galaxy's apparent diameter than to its inner brightness. A galaxy can become enormous in extent while remaining relatively unchanged at its heart. In a dense cluster core, even a flyby can be damaging because relative speeds are high and encounters are frequent. Tidal forces stretch a satellite, pulling stars into leading and trailing tails, even if no merger happens immediately. Repeated encounters can pre-strip a galaxy before it ever reaches the center, delivering it as a weakened meal. As satellites are stripped, their gas is also vulnerable, and the cluster provides a second weapon. The hot intracluster medium exerts ram pressure, pushing gas out of infalling galaxies like wind-ripping leaves from a tree. Star formation shuts down, disks fade, and the cluster converts spirals into redder, quieter systems that are easier to assimilate. So the cluster environment prepares the food, and it does so with multiple tools acting at once. It removes gas, heats orbits, and reduces the ability of small galaxies to remain coherent. By the time they reach the central region, many are already half dismantled, carrying their stars like loose cargo. The cannibalism leaves evidence, and the evidence is not subtle in principle, even if it is faint in practice. Stellar streams arc through halos as thin ribbons of disrupted satellites, sometimes forming great circles around the host. Shells appear as nested ripples, created when stars from a swallowed galaxy phase wrap in the new potential. Phase wrapping is a simple idea with a haunting visual outcome because stars from the disrupted system spread along their orbits. Where many of them reach epicenter at similar times, they pile up and brighten, forming sharp-edged arcs. The shells look like ripples on a pond, except the pond is gravity and the ripples are stars. These features are transient on cosmic timescales, but they can persist for billions of years in low-density outskirts. Over time, streams thicken and dissolve into a smooth glow, turning a violent event into a quiet brightness profile. The smoothness of a giant halo can be the end state of many erased scars. Around CD galaxies, the crime scene tape is often diffuse rather than sharp because the outer regions are a mixing bowl. The halo can be enormous, and it can align with the cluster potential more than with the inner galaxy. That alignment hints that the outer envelope is built from cluster-scale processes, not only one galaxy's internal evolution. Intra-cluster light is part of that tape, and it is one of the hardest components to measure cleanly. It is starlight from stars no longer bound to any single galaxy, stripped by tides and harassment during repeated encounters. In cluster centers, intra-cluster light can overlap the CD envelope until the boundary becomes a question of dynamics, not appearance. Either way, the photons tell the same basic story, even if the bookkeeping changes. Those stars were born in smaller systems, then removed by gravity, then redistributed into a larger structure. The faintness of the halo is not gentleness, and it is not emptiness. It is dilution after violence. This overlap matters for IC 1101's terrifying scale, because the definition of galaxy becomes slippery at the edges. If much of the outer light is bound to the central galaxy, then it is a direct monument to accretion. If much is intracluster, then the cluster itself is a shredder, and the central galaxy sits inside a shared stellar ocean. Now connect the mechanisms to the setting we already established, because environment is not a footnote here. Abell 2029 is massive, relatively relaxed, and centrally concentrated in X-rays, which implies a deep potential and a dense hot atmosphere. A deep potential increases orbital speeds, but it also increases the supply of satellites and the frequency of close passages. In the core, the central galaxy sits near the bottom of the potential well, where orbits naturally crowd. Satellites on plunging trajectories experience strong tides and strong dynamical friction, and they rarely get a second chance. The cluster acts like a funnel, and the central galaxy acts like the drain. Over billions of years, the drain accumulates layers, and those layers do not all look the same. Some layers come from major mergers that set the basic elliptical structure early, when the universe was more merger-rich. Other layers come from minor accretion that inflates the envelope, building the extended light that makes IC 1101 feel less like a galaxy and more like a region. This is why the universe builds big things by assembling smaller ones over time, rather than forming them in a single monolithic collapse. It is easier to grow by addition than by forming everything at once, because cooling, star formation, and feedback limit how fast a single object can create stars. Mergers bypass those limits by importing stars already made, already aged, already counted. Historically, this idea replaced an older intuition that giant ellipticals formed in one rapid event and then simply faded. Observations of faint tidal features and the rise of cosmological simulations pushed the field toward assembly as an ongoing process. The modern picture is less tidy, but it matches what gravity naturally produces. The result is a galaxy whose stellar population can be old even while its size keeps increasing, which sounds like a contradiction until you separate stars from structure. The stars formed early in many places, then were rearranged late into one dominant system. IC 1101 can look ancient in colour, yet still be a recent product in shape. There is a second kind of evidence, and it is statistical rather than photographic, which makes it harder to feel but harder to dismiss. Ellipticals in dense environments follow scaling relations that encode merger history, linking size, luminosity, and velocity dispersion. Size can grow faster than mass during minor accretion, which pushes giants to extreme radii for their luminosity. Central dominants also show multiple structural components in their brightness profiles, as if the galaxy is layered like sediment. An inner body can resemble a normal giant elliptical, while an outer envelope follows a different slope and extends much farther. That break can mark the transition from galaxy-built stars to accreted and stripped stars. Even the kinematics can carry fingerprints, because motion remembers what light tries to hide. The outer halo can rotate differently from the core, or show increased velocity dispersion, consistent with accreted material on varied orbits. The outermost stars can behave more like cluster traces than like a self-contained system. Now confront the word that makes this chapter unsettling, because language shapes what we think we are seeing. Cannibalism implies intention, but gravity has none, and that is the point. The process is automatic, and the victims are chosen by mass, orbit, and proximity, not by malice. In a crowded cluster, survival is temporary, and stability is often just a long delay. A small galaxy can orbit for a while, but repeated encounters heat and strip it until it unravels. A massive satellite can resist longer, but dynamical friction targets it more strongly, pulling it inward until the merger becomes unavoidable. The central galaxy grows like a predator because the environment makes it one, and because the rules reward the already massive. The cluster delivers prey, the physics removes escape routes, and time finishes the job. IC 1101 is terrifying because it suggests that, given enough time, the center wins. But mergers do not only add stars, and this is where the story tightens toward the core. When galaxies merge, gas can be driven inward by tidal torques, even in systems that are mostly gas-poor. That inflow can feed the central supermassive black hole, and the black hole can respond violently. A black hole does not need much mass to change a galaxy's fate, because accretion is an efficient engine. Accretion converts a fraction of mass into enormous energy, released as radiation and jets that can outshine the galaxy briefly. That energy can heat surrounding gas, prevent cooling, and shut down future star formation, locking the system into an old red state. In cluster centers, this feedback can couple to the hot atmosphere in ways we can actually see. Jets can inflate cavities in X-ray gas, dark bubbles surrounded by bright rims, stirring and reheating the intracluster medium. The black hole becomes a thermostat, regulating cooling flows that would otherwise dump fresh gas into the core. So the merger history and the black hole history become one story, braided together by cause and consequence. Mergers build the galaxy's mass and deliver fuel, sometimes as gas, sometimes as stars, sometimes as destabilized orbits. The black hole's outburst can then freeze the galaxy's growth in new stars, even as the galaxy keeps growing in size through accretion of existing stars. This is the pivot toward the next chapter's danger, because the center is not passive. The same process that builds IC 1101 also builds an engine at its center, an engine capable of shaping the entire cluster core. The galaxy becomes both a graveyard of neighbors and a regulator of its environment. Return to the central question with new weight, because the scale now has a mechanism behind it. IC 1101's size is not just a measurement challenge, or a catalogue curiosity that depends on where you draw the edge. It is a consequence of hierarchical assembly operating at the richest intersection of the cosmic web. The opening hook becomes more than scale shock, and it becomes a quiet moral about accumulation. If dozens of Milky Ways could fit inside one halo, then dozens of histories were ended to build it. The glow is not only starlight, and it is not only beauty, it is accumulated biography, stripped and blended until individuality disappears. One transition carries us forward, because the outer halo is only the first half of the monster. To understand the monster's present, we have to follow what mergers trigger in the core, where black holes, hot gas, and feedback decide what kind of giant survives. From here, we move from the galaxy's outer crime scene to its inner engine. We follow the fuel lines that mergers open, and we ask what wakes up at the center when the feeding never stops. From here, we move from the galaxy's outer crime scene to its inner engine. IC 1101's scale is written in faint starlight, but its power is written in darkness. On screen, the camera abandons the ghostly halo and dives inward, past diffuse stars, toward a core that looks calm, yet is anything but. At the centre sits a supermassive black hole, defined by one boundary we cannot cross. The event horizon is not a surface, but a point of no return. It is a geometric boundary in space-time, an edge where escape speed reaches light speed, and every possible future points inward. Outside that horizon, gravity still allows matter to orbit, collide, and heat. That heating is the first unsettling twist, because darkness can generate light. In a visual sense, it is like watching a black pit surrounded by a bright rotating ember ring, light created by matter's last desperate friction. A black hole is black only when it is starving. When it feeds, the surrounding gas becomes an accretion disk and the disk becomes a furnace. The disk is not a neat vinyl record, but a churning layered flow, dense in the midplane, hotter and thinner above and threaded with magnetic structure. Gas spirals inward because it must lose angular momentum, and friction does that work. In practice, turbulence and magnetic fields turn orbital energy into heat. The key mechanism is often magnetorotational instability, MRI for short, which turns weak magnetic fields into an efficient brake, letting gas drift inward while energy rises outward. The inner disk reaches extreme temperatures, radiating across optical, ultraviolet and X-ray bands. The black hole itself emits nothing, yet the infall can outshine entire galaxies. In the most luminous phases, the disk's inner regions glow so fiercely that the spectrum shifts into hard X-rays, light that can pierce gas clouds and reveal the engine's presence. This is not a violation of physics, but a consequence of efficiency. Accretion can convert a large fraction of rest mass into radiation before matter disappears. For a spinning black hole, the efficiency can climb toward a few tenths of the infalling mass energy, an astonishing return for gravity alone. Nuclear fusion in stars is powerful but comparatively stingy, releasing less energy per kilogram. Accretion is gravity's shortcut, extracting energy from the plunge. In plain terms, a star must patiently build energy in its core, while a black hole gets paid up front by shredding and heating matter as it falls. Some of that energy does not leave as light, and that is where the monster grows teeth. Many feeding black holes launch jets, narrow beams moving near light speed. These jets are not simple streams, but relativistic outflows, plasma guided by magnetic fields, carrying kinetic energy, momentum, and ordered electromagnetic structure far beyond the nucleus. Jets are not guaranteed, but they are common when magnetic fields thread the disk. The fields can tap rotational energy and collimate plasma into long, stable outflows. In the leading models, twisted field lines act like a cosmic dynamo, extracting energy from the disk or even from the black hole's spin, then focusing it into two opposed, needle-thin channels. A jet does not need to hit many stars to matter. It only needs to couple to gas, because gas is the reservoir that makes future stars. When the jet shocks and stirs that gas, it changes pressure and temperature, and it can keep the material from cooling into the dense clouds that would otherwise collapse. So the core of ICLN-01 is not only a graveyard of mergers, it is also a regulator, an engine that can decide whether the galaxy keeps forming stars. Visually, the story shifts from star fields to invisible forces, arrows of energy, ripples in hot gas, and cavities carved into a medium we cannot see with human eyes. Now connect the black hole to the galaxy that hosts it, because the relationship is not random. Across the universe, bigger bulges tend to host bigger central black holes. This idea crystallized in the late 20th century, when improved spectroscopy let astronomers measure stellar motions in galaxy centers with enough precision to weigh the unseen. Astronomers see correlations between black hole mass and stellar velocity dispersion, and also with bulge mass. These scaling relations suggest coevolution, not coincidence. The dispersion, how fast stars swarm in random directions, acts like a thermometer for the bulge's gravitational depth, and the black hole appears to know that depth. The details are still argued, but the trend is clear enough to be predictive. If a galaxy is among the most massive known, its black hole is expected to be enormous. In IC1101, that implication becomes hard to hold in the mind, because the numbers are both precise and absurd. We're talking about billions of solar masses, compressed into a region smaller than the solar system. A billion solar masses means gravity dominates everything nearby, even dense star clusters. It means orbital speeds near the center become extreme, and time itself runs differently. Clocks deeper in the potential tick more slowly relative to faraway observers. It also means the black hole's sphere of influence can be large by galactic standards. Within that region, stellar motions trace the black hole's mass more than the galaxy's broader potential. Observationally, astronomers search for a sharp rise in velocity dispersion toward the centre, and for orbital patterns that cannot be explained by stars alone, yet the black hole is still tiny compared to the galaxy's full extent. That contrast is part of the unease, because a small centre can steer a vast system. On screen, it is a dot commanding a continent, an invisible point whose decisions echo across hundreds of thousands of light years. How does such a black hole grow to that scale? The simplest answer is the same one we used for the galaxy, repeated at smaller radii. Black holes grow by accretion, and they grow by mergers with other black holes. Both pathways are triggered by the same events that build seedy galaxies, because cluster centres are where collisions become routine. When galaxies merge, their gas does not stay politely in orbit. Tidal torques and shocks drain angular momentum, funneling gas toward the nucleus. The gas can form bars and streams, then crash into itself, radiating energy away until it settles into the central few hundred parsecs, close enough for the black hole to feed. Even in systems that are gas-poor today, mergers in the past could deliver fuel. Early epochs had more cold gas, and cluster centres had more infill. The universe was younger, denser, and more chaotic, and the same gravity that assembled IC 1101's envelope likely delivered repeated meals to its core. As gas piles up, the accretion rate can rise toward the Eddington limit. That limit is a balance, where radiation pressure pushes outward as gravity pulls inward. In simple language, there is a brightness so intense that photons shove back on the inflowing gas, and the black hole's own light becomes a self-regulating barrier. At high rates, the nucleus becomes an active galactic nucleus, or AGN. The galaxy's brightest phase can be powered by a region smaller than a pixel. If we could see it up close, the centre would look like a compact beacon, blinding, variable, and surrounded by fast-moving gas that leaves broad spectral lines as a signature. The unsettling part is that the brightest engines are born from invisible darkness. A black hole announces itself only by what it destroys and what it energizes. The light is not the monster itself, but the scream of matter as it is compressed, heated and stripped of its last stable orbits. Now bring in the second growth channel, because IC 1101 is built from repeated mergers. If galaxies merge, their central black holes should eventually meet. After a merger, two black holes sink toward the new centre through dynamical friction. They lose orbital energy to stars and dark matter, forming a bound binary that tightens over time. That binary is not just a detail, because it changes the galaxy's core. As the pair hardens, it can eject stars through gravitational slingshots, scouring out a low-density centre. Each close encounter flings a star outward like a pinball shot, stealing orbital energy from the binary and leaving behind a shallow, depleted core. Giant ellipticals often show these depleted cores, and seedy galaxies can show them strongly. The core becomes a fossil imprint of past black hole pairing. In images, that imprint appears as a subtle flattening of the central light profile, an absence that tells a story, even when the protagonists remain unseen. As the binary tightens further, gravitational waves become the dominant energy loss channel. The system radiates space-time ripples carrying away orbital energy and angular momentum. Those ripples are not metaphorical. They are real distortions predicted by general relativity, propagating at light speed, and they carry information about mass, spin, and orbital geometry. We should be careful with promises, because detection depends on mass, distance, and frequency. But in principle, the biggest mergers in cluster centers are prime gravitational wave sources. Future space-based detectors aim for that band, where supermassive binaries chirp slowly, and where the signal can build over months or years rather than seconds. Even without a direct detection, the theory links mergers to black hole growth. There is another complication that makes the story darker. If the merger is asymmetric, the final black hole can receive a recoil kick from uneven wave emission. The remnant is not guaranteed to sit politely at the centre. It can be jolted like a cannon recoil by the momentum carried away in gravitational waves. A strong kick could displace the black hole from the centre, at least temporarily. In the most extreme cases, it could even escape, though massive cluster cores make escape harder. Whether or not IC 1101 experienced such a kick, the possibility matters, because it reminds us that even the central engine can be moved by invisible physics. Now return to the scaling relations, because they are not just statistics. They are a clue that the galaxy and its black hole regulate each other over time. If the black hole grows too quickly, its energy output rises. That output can heat gas, drive winds, and prevent the next generation of stars. This is feedback, and it is one of the most important ideas in modern galaxy formation. Without feedback, models overproduce stars and fail to match observed galaxies. In simulations, gas cools too efficiently, collapses too readily, and turns into stars until galaxies become unrealistically bright and compact, unless an engine injects energy back into the system. Feedback comes in two main modes that can overlap. There is radiative or quasi-mode feedback, and there is jet or radio mode feedback. Radiative feedback is strongest when accretion rates are high. Intense radiation can ionize gas, push on dust, and launch outflows that clear the nucleus, sometimes at thousands of kilometers per second. Jet feedback is often associated with lower accretion rates in massive ellipticals. The black hole feeds more quietly, yet launches jets that deposit mechanical energy far out. The energy arrives not as a flash, but as persistent work, punching cavities, driving weak shocks, and keeping hot gas from settling into a dense star-forming reservoir. In a cluster like Abell 2029, jet feedback can couple to the hot intracluster medium. The jets inflate bubbles, stir turbulence, and offset radiative cooling. In X-ray images, those bubbles can appear as dark cavities against a bright hot atmosphere, like fingerprints pressed into glowing fog, marking where the jets have done their work. This matters because clusters should cool rapidly in their cores if left alone. Hot gas radiates X-rays, loses energy, and should flow inward in a cooling flow. The physics is straightforward. If a plasma radiates away its thermal energy, pressure drops, gravity wins, and gas should sink toward the center. If that cooling proceeded unchecked, cold gas would accumulate and form stars at high rates. Many cluster central galaxies would be blue and star-forming, yet most are not. Instead, many are red and dead, dominated by old stellar populations. They can still grow by cannibalism, but they form few new stars, and their light is the warm glow of ancient suns. The black hole is a leading suspect for why. It can act like a thermostat, injecting energy when cooling tries to restart the flow. The thermostat analogy is imperfect, but the cycle is plausible. Cooling increases central gas density. Density feeds the black hole, and the black hole heats the gas again, an intermittent pulse rather than a steady flame. This is a feedback loop that can run for billions of years. It is not gentle, and it does not need to be constant to be effective. A brief outburst can reheat the core, raise entropy, and delay cooling for hundreds of millions of years, which is long enough to change the galaxy's entire future. The result is a galaxy that grows in mass while its star formation is suppressed. It becomes larger by adding existing stars from victims, not by making many new ones. That is why ICL-1 can be enormous and still look old. Its halo can expand through minor mergers, while its core remains quiescent in star formation, like a city expanding by absorbing neighbouring towns rather than building new neighbourhoods. Feedback also helps explain why the most massive galaxies are not the most luminous in young stars. The engine at the centre can shut the door on fresh fuel. It is a strange accounting. The more massive the system becomes, the more effectively it can prevent itself from shining with youth. Now connect this back to the documentary's central question, because the engine is part of the assembly story. How did IC1101 become so large, and what does that reveal? It reveals that growth is not only additive, but also suppressive. The same mergers that deliver stars and gas can trigger the black hole that prevents new stars, turning a potential starburst into a quenched, aging giant. It reveals that the brightest phases of a giant galaxy may be brief and violent. A quasar episode can flare, reshape the gas, then fade into quiet radioactivity. In the visual language of the film, the core flashes like a lighthouse, then dims, leaving behind only the slow, patient sculpting of jets and hot plasma. It also reveals that the most important structures are often the least visible. The black hole is unseen, the jets can be faint, and the consequences are written in missing stars. When a core is scoured, when gas refuses to cool, when star formation stalls, we're reading a negative image, evidence defined by what is absent. There is a deeper unease in that accounting. A galaxy can look calm because the violence is in the past, and because the engine hides behind an event horizon. We can infer the black hole's mass from stellar motions and from scaling relations, but we cannot see the horizon directly at this distance. the centre remains a hypothesis with teeth, supported by dynamics, spectra, and the stubborn consistency of physics. Even the language is a trap because we call it a hole as if it were empty. It is not emptiness, but a concentration of mass that bends the rules of ordinary intuition. The black hole is not a vacuum cleaner roaming the galaxy. It is a compact gravitational well, and only matter that ventures close enough is doomed. Now widen the frame again, because the black hole is not acting in isolation. Its jets and radiation interact with gas that belongs to the cluster as much as to the galaxy. In Abell 2029, the hot atmosphere is massive and pervasive, outweighing the stars. That gas is the medium through which feedback propagates, and the medium is cluster scale, filling the space between galaxies like an invisible ocean. So the black hole can shape conditions far beyond the visible core. It can influence cooling, pressure, and entropy in the central intracluster region. In physical terms, it changes the thermodynamic state of the plasma, raising temperature, redistributing density, and preventing the runaway condensation that would otherwise feed star formation. That influence can indirectly shape future accretion onto the galaxy. If the gas stays hot, it resists condensation, and the galaxy's growth shifts toward dry mergers. Dry mergers add stars without adding much cold gas, and they preserve the red, dead character. They also build extended envelopes efficiently, especially in cluster centers, where satellite galaxies are constantly being stripped and absorbed. This is the paradox at the heart of the monster. The black hole can starve the galaxy of new stars, while the cluster keeps delivering old stars to be absorbed. The galaxy becomes a collector of stellar history, and the black hole becomes the warden of its gas. The brightest engines are born from invisible darkness, then they enforce silence, an empire built on both consumption and restraint. Now we need to be precise about what the black hole can and cannot do. It can regulate gas and star formation, but it cannot create millions of light-years of envelope by itself. The outer halo is too large to be explained by nuclear physics alone. The envelope scale points to the cluster's gravitational architecture, not only the galaxy's nucleus, and that architecture is written in mass we do not see. A black hole can heat and stir, but it cannot hold a 6 million light-year boundary together. Something larger provides the binding, and it does so invisibly. That larger thing is the cluster potential, dominated by dark matter. The galaxy sits at the bottom of a much bigger well, and the well defines the stage, setting the orbits, the infall, and the long-term fate of everything luminous. So the chapter ends with a shift in responsibility. The heart is powerful, but the body is held by something even more massive and more hidden. Next, we follow that hidden mass outward, from the black hole's immediate influence to the cluster's full gravitational grip. We ask what holds Abell 2029 together, and what that implies for IC 1101's true size. A black hole alone can't build a 6 million light-year envelope. Something larger holds the whole cluster together. We zoom out from IC 1101 and the scale shock changes shape, because the frame finally catches up to the physics. The galaxy stops being a lone monster and becomes a downtown landmark, bright at the center of a much larger map. In the wide shot, the background fills with other galaxies, faint smudges and needles of light, each one a separate island universe. The camera keeps pulling back until the emptiness between them becomes the story, because that empty space is where most of the cluster lives. Abell 2029 is a galaxy cluster, a bound city of matter on megaparsec scales. It is hundreds to thousands of galaxies sharing one deep gravitational well, and that well is the real architecture. The cluster is not a decorative arrangement, and it is not a temporary crowd. It is one of the largest structures in the universe that remains gravitationally bound, meaning it has enough mass to resist cosmic expansion locally. That single fact is already unsettling, because it tells us gravity can still win, even in a universe that is stretching. A cluster is not a loose association like a small group, where a few galaxies drift around a common center. In a group, typical speeds are modest, and encounters can be slow enough to merge gently. In a rich cluster, velocities rise to hundreds, or even over 1,000 kilometers per second, and the environment becomes harsher. The distances inside a cluster are measured in millions of light years, and the travel times for galaxies are measured in billions of years. When we say orbit, we mean a path so long that a single circuit can outlast the rise and fall of species on Earth. If we could see Abell 2029 as a three-dimensional model, we would notice it is not a neat sphere. It has substructure, clumps, filaments, and in falling groups, because clusters grow by accreting along the cosmic web. That web is the universe's large-scale scaffolding, where matter collects in strands and knots. Abell 2029 sits at one of those knots, and that placement matters. The cluster is not merely a container for galaxies, it is an endpoint for flows of matter that have been converging for most of cosmic history. The galaxies are the obvious citizens, but they are not the main mass, and they are not even the main normal matter. The cluster's dominant baryonic component is hot gas between galaxies, spread so thin that it would pass for vacuum in a laboratory. Yet on these scales, thin still adds up to enormous mass. This gas is the intracluster medium, a plasma heated to tens of millions of degrees by gravitational infall and repeated shocks. At those temperatures it shines in X-rays, not visible light, because electrons and ions collide violently enough to radiate at high energies. Imagine the visuals. A visible light image shows a swarm of galaxies, each one crisp and separate. Then an X-ray overlay fades in like a ghostly fog, filling the space between them with a luminous bluish haze. The brightest X-ray glow pools toward the center, as if the cluster were a bowl holding a hot invisible fluid. That glow is not decoration, it is a measurement. X-ray brightness maps density, because brighter regions mean more emitting particles along the line of sight. X-ray spectra map temperature, because hotter gas shifts the emission signature and changes the balance of spectral lines. The physics behind that glow is both simple and brutal. In a hot plasma, electrons are stripped from atoms, and their collisions produce bremsstrahlung radiation, breaking light, when charged particles are deflected. Heavy elements add their own fingerprints, because ions like iron and silicon emit characteristic lines. Those lines are not just pretty data points, they're a record of enrichment. They tell us that generations of stars lived, died, and seeded the intracluster medium with metals, which were then stirred and spread by cluster-scale turbulence. From density and temperature, astronomers infer pressure and how it changes with radius, and pressure is where the story becomes quantitative. If the gas is close to hydrostatic balance, pressure traces gravity, because the gas must push outward to resist the inward pull of the cluster's mass. This is how clusters are weighed without touching them, using the gas as a test particle that fills the potential well. The hot gas sits in the well and reveals the depth of the well, the way water reveals the shape of a basin. The method is not perfect, because mergers and turbulence can disturb the gas, but in relaxed cores it becomes remarkably powerful. There is history in this technique, because X-ray astronomy itself is a young sense. For most of human time, clusters were only optical curiosities, dense patches of faint galaxies catalogued by their positions. Only in the late 20th century did satellites above Earth's atmosphere reveal that clusters are X-ray beacons. That discovery changed the definition of what a cluster is, because it showed that the space between galaxies is not empty. It is a hot, dynamic medium that carries most of the baryons, and it behaves like a weather system on cosmic scales. Abell 2029's X-ray glow is centrally concentrated and smooth enough to suggest a mature core. Mature does not mean peaceful, it means the violence is mixed, and the scars have been blurred by time. In a young cluster, you expect jagged edges, multiple peaks, and obvious shock fronts from recent collisions. In a mature cluster, the gas can settle into a more symmetric shape, with gradients that look almost engineered. That smoothness is a kind of forensic evidence because it implies the last major disruption happened long enough ago for the gas to relax. Clusters are violent ecosystems because their gravity accelerates everything, and because the scale makes every interaction energetic. Galaxies fall in fast, pass close, and get stripped even without direct mergers, because the cluster's tidal field is relentless. The intracluster medium adds another kind of violence, one that does not require a collision of stars. It exerts ram pressure, an aerodynamic force, on an infilling galaxy's gas disk. If the galaxy is moving quickly enough through dense enough plasma, that pressure can peel away cold gas like wind tearing leaves from a branch. In visuals, you can picture a spiral galaxy entering the cluster like a ship entering a storm. Its gas trails behind in a faint comet-like tail, while the stellar disk remains mostly intact. Star formation dims as the fuel is removed, and the spiral's blue knots fade toward red. This is one pathway to the cluster's population shift, where spirals become rarer and ellipticals dominate. The transformation is not only about merging, it is also about starvation, stripping, and the slow shutdown of new stars. The cluster also produces tidal forces that stretch galaxies as they orbit, and those tides do not care about beauty or symmetry. Repeated encounters heat stellar disks and turn ordered rotation into random motion, a process sometimes called harassment. A galaxy can survive the encounters and still be changed, because its internal structure absorbs the impacts like a bell absorbing repeated strikes. Over time, thin disks thicken, bars can weaken, and outer stars can be lifted into diffuse halos. The cluster is not just a stage for galaxies, it is an engine that edits them. So Abell 2029 is not just a container for galaxies, it is a machine that transforms them, then recycles their stars into the centre, and that recycling is the key to IC 1101. This is where IC 1101 stops looking like an isolated freak. It looks like the natural occupant of the deepest gravity crater, the place where the cluster's long-term bookkeeping ends up written. If you want to build a galaxy with an absurdly extended envelope, you do not start with one merger. You start with a city that keeps sending you material. In a cluster, orbits are not evenly distributed, because the potential funnels mass inward, and the centre becomes a meeting point for decaying trajectories. The mathematics of this is phase space, the combined space of positions and velocities, where stable configurations are rare. Over time, the cluster tends toward a state where energy is redistributed, and massive objects lose orbital energy more efficiently. Dynamical friction is the quiet accountant of that funnel. Massive satellites raise gravitational wakes in the surrounding matter, stars, gas, and dark matter, and those wakes tug backward, stealing momentum. This is not friction like rubbing hands together, but it has the same consequence. Motion is converted into heat and disorder in the background medium. The satellite slows, its orbit shrinks, and its path becomes more radial, delivering it toward the centre. The cluster sorts by mass, then delivers the biggest pieces to the core first, because the heaviest galaxies create the strongest wakes. The central galaxy becomes the place where infall ends, not by decree, but by dynamics. The centre is where sinking orbits terminate, because it is where potential energy is lowest. That central galaxy type has a name, because it appears again and again across the sky. It is the CD galaxy, the central dominant elliptical, and the label carries history from early cluster studies. Observers noticed that some clusters have a brightest cluster galaxy that is not merely the brightest. It is qualitatively different, larger, more diffuse, and surrounded by a faint extended envelope that seems to merge into the cluster itself. The C originally suggested central, and the D suggested diffuse, which is exactly what the eye sees in deep images. CD galaxies are not simply large ellipticals scaled up like a photograph enlarged on a screen. They have extended envelopes that blend into intra-cluster light and track the cluster's overall potential, so the outer stars are less like a private property line and more like a public shoreline. The inner body can look like a standard giant elliptical, built early and violently. The outer halo looks like accumulated debris, built late and repeatedly, and that two-part structure is the clue. It tells us the galaxy's history is not a single event but a long sequence of additions. This layered structure resolves a key tension from earlier chapters. The boundary of IC 1101 is not a clean edge, it is a transition zone, where the brightness falls so low that definitions begin to matter. Some of the faint outer light is bound to the galaxy, and some belongs to the cluster. The measurement depends on depth, subtraction, and definitions of membership, because observers must decide where galaxy ends and intra-cluster begins. In practice, that decision can shift the reported size dramatically, and it is why different studies can quote different extents. But the physical origin points in one direction. The outskirts are built by stripping and minor accretion in the cluster core, where tides are strongest and encounters are frequent. When a satellite approaches the centre, tides pull stars into streams and shells, and those structures can wrap around like pale ribbons. Those stars can remain loosely bound, inflating the halo without brightening the core, because the added light is spread over an enormous area. When the satellite is fully disrupted, its stars become intracluster light, and that light is a shared stellar ocean. It is brightest near the centre, where disruption happens most often, and where debris spends the most time. In deep imagery, intracluster light looks like a faint mist between galaxies. a glow that refuses to resolve into a single object. It is difficult to photograph because it sits near the limits of sky subtraction, where instrumental effects can masquerade as structure. Yet when it is measured carefully, it becomes a map of past violence. Each stripped stream is a sentence in the cluster's diary, and each smooth region is what happens after the ink has been smeared by time. The more relaxed the cluster, the more the diary reads like a palimpsest, many stories written over one another. In practice, the CD envelope and intracluster light overlap until bookkeeping becomes dynamical. The question becomes which stars orbit the galaxy and which orbit the cluster, and the answer can change with radius. Near the centre, stars respond mostly to the galaxy's own potential. Farther out, the cluster's potential dominates, and the stars behave like traces of the cluster as a whole. Either answer keeps the central question sharp. IC 1101 becomes enormous because Abell 2029 keeps delivering material to the same address, and because the address sits at the bottom of the deepest well. The cluster's deep well also explains why the biggest galaxy sits at the centre, and why it stays there once it arrives. The centre is not a privileged location because it is bright. It is privileged because it is stable, and because energy naturally drains toward it in a system that can exchange momentum. This is not a coronation by beauty or brightness. It is a consequence of phase space, friction, and a long supply chain, and the supply chain runs for billions of years. The cluster is patient, and patience is a kind of power. Time is the key ingredient, and it behaves like a character in this story, one that never speaks but always acts. It does not act quickly, but it never stops applying the same rules, and those rules are cumulative. Over billions of years, galaxies pass through the core again and again. Each passage removes a little energy, a little angular momentum, a little structure, and the losses add up. In a single encounter, the change can be subtle. Over 100 encounters, the change becomes destiny. Some encounters end as major mergers that scramble stellar orbits and build a pressure-supported spheroid, the classic elliptical shape. In those events, ordered rotation is converted into random motion, and the remnant becomes rounder and smoother. Others end as minor mergers that puff up the outskirts, because small companions deposit stars at large radii. The difference matters because it explains how a galaxy can grow in size without dramatically increasing its central density. It also explains why the core can look old and settled while the halo keeps expanding. The timeline matters for what we can test, because different epochs leave different signatures. Early major mergers set the core's old stellar population and its smooth elliptical shape, and they can also build a central supermassive black hole through accretion and black hole coalescence. Later, minor accretion adds stars at large radii and steepens the size growth, and those stars can have slightly different chemical fingerprints. That is how a galaxy can look ancient in colour, yet keep expanding in extent, like an old city that keeps adding suburbs. Observable signatures follow from that two-phase build, and astronomers look for them with both light and motion. Brightness profiles can show breaks between inner galaxy and outer envelope, where the slope changes as the dominant component shifts. Kinematics can show the outer stars behaving more like cluster traces than like a self-contained galaxy. Because the cluster's gravity begins to dominate their motions, the velocity dispersion can rise with radius, and rotation can decouple, signalling that the outer halo is not simply an extension of the inner body. Tidal debris can persist as faint shells and streams, then dissolve into a smooth glow, and the timescale depends on orbit and environment. In a dense core, mixing can be efficient, because repeated perturbations scramble coherent structures. Smoothness becomes evidence of many erased collisions, not of calm, and that inversion is one of the chapter's quiet twists. A cluster core can look serene in a photograph precisely because it has been violent for so long. The violence has been averaged into symmetry. Abell 2029 also tells us why the process is efficient here, because not all clusters build giants equally. The core is dense, the encounter rate is high, and the supply of satellites is continuous, fed by infall along surrounding structure. Even galaxies that never merge directly can be pre-processed, meaning they are altered in smaller groups before they ever reach the cluster. Harassment and stripping weaken them, then the centre finishes the job, and the debris is added to the growing envelope. The city does not need to swallow every building whole to grow. It can grow by grinding them down. This is the city that built the giant, and it built it by demolition. The cluster turns individual galaxies into a common pool of stars, and then gravity concentrates part of that pool back into the centre. The result is a central galaxy with an envelope so extended that it challenges our intuition about what a galaxy even is. When we say IC 1101 is enormous, we're also saying the cluster is efficient at moving mass inward. The giant is not an exception to the cluster, it is a signature of the cluster. Now return to the opening hook and let it land differently. If the Milky Way could fit inside one galaxy, then the cluster is the factory that made room, and the factory runs on time. IC 1101's terrifying scale becomes less like a miracle and more like an outcome. Put enough mass in one well and wait long enough and the centre wins, because gravity is a strategist that never tires. The question that lingers is not whether this can happen. The question is how often and what it costs the surrounding galaxies. The intracluster medium keeps the story from becoming only about stars, because the gas dominates the baryonic mass and records the cluster's thermodynamic history. Because it emits X-rays, it reveals shocks, cooling and heating cycles, and those cycles are the cluster's metabolism. It shows where energy has been injected and where gravity has compressed the plasma, and it shows how quickly the core would cool if nothing opposed it. In many clusters, the central gas should cool rapidly enough to form stars in a cooling flow, yet the observed star formation is often too low, implying that heating must intervene. That connects back to the previous chapter's engine. The central black hole can inflate cavities and stir the hot gas, altering cooling in the core, and those cavities can appear as dark bubbles in X-ray images. They're not empty in a literal sense, but they are under dense regions filled with relativistic particles and magnetic fields pushed outward by jets. As the bubbles rise, they can drive weak shocks and sound waves, distributing energy through the core. The feedback is subtle and persistent, like a thermostat that prevents runaway cooling without blowing the system apart. So the cluster is a coupled system, not separate parts. Galaxies feed the center feeds back into the gas, and the gas shapes future infall by stripping and pressure. The pieces talk to one another through gravity and through plasma physics, and the conversation lasts for billions of years. When we look at Abell 2029, we are not seeing a snapshot of static objects. We are seeing a long negotiation between collapse and resistance, between cooling and heating, between assembly and disruption. Abell 2029's deep potential also sets the stage for the most unsettling accounting, the one that refuses to balance. The gravity inferred from motions and hot gas exceeds what stars and gas can supply, even when we are generous with the estimates. Even if we count every galaxy and every atom of plasma, the numbers do not balance. The cluster behaves as if most of its mass is invisible, and that invisibility is not a minor correction. It is the dominant term in the equation. This discrepancy is not new, and it has a lineage that runs back through the history of astronomy. When astronomers first measured galaxy velocities in clusters, the speeds were too high to be held by visible matter alone. Later, X-ray measurements strengthened the case, because the hot gas also required a deep potential to remain bound. Different methods, light, motion, and plasma, converged on the same conclusion, which is why the problem became impossible to ignore. The missing mass is not a trick of one instrument, it is a property of the cluster. This is the transition that changes the documentary's stakes. Visible matter can't explain the cluster's gravity, so we follow the missing mass. Next, we step into the dominant ingredient that holds Abell 2029 together. We enter the dark matter halo that makes a gravity crater deep enough to build IC 1101. Visible matter can't explain Abell 2029's gravity, so we follow the missing mass. On screen, the cluster looks calm, an island of galaxies pinned against a black ocean, yet every orbit and every temperature reading says it is heavier than it appears. The galaxies, the hot X-ray gas, even the central black hole together still come up short. Add the starlight, add the plasma, add the compact mass in the core, and the numbers refuse to balance. The cluster behaves like it is filled with weight we cannot see, as though the light is only a skin. Dark matter is that weight, inferred by what it does to motion and light. It does not glow, absorb, or reflect in any ordinary way, so telescopes don't see it directly. It announces itself through gravity, and gravity never needs permission to act, only mass to respond. Historically, this idea did not arrive as a single revelation, but as an accumulating discomfort. In the 1930s, Fritz Zwicky studied the Coma cluster and found galaxy speeds that implied far more mass than the light suggested. His phrase, missing mass, sounded almost like an accounting error until the universe kept repeating it. The first clue comes from galaxies that should not hold together, at least not for long. In spiral galaxies, stars far from the centre orbit too fast, tracing wide circles through faint outer disks. If only visible matter mattered, outer stars should slow down with distance, following a Kepler-like decline. Instead, the rotation curves stay flat, as if an unseen halo adds mass outward. The data look like a stubborn refusal of physics to behave, until you remember that physics is behaving perfectly, just not with the matter you can see. The outer stars move as though they are embedded in a much larger, heavier structure. This is not a small correction at the edge of the data, and it is not a quirk of one galaxy type. The discrepancy is systematic across many galaxies and environments, from bright spirals to dim dwarfs at the edge of detectability. The simplest reading is that most of a galaxy's mass is not in stars. The light is the decoration, and the gravity is the structure. Visually, imagine a luminous pinwheel painted on a transparent disk, while an invisible sphere of mass extends far beyond it. The starlight ends where the camera fades, but the gravitational influence continues, quietly shaping every orbit. Clusters make the problem impossible to ignore, because they are bigger and harsher. In a rich cluster, galaxies move at hundreds to over 1,000 kilometers per second, flashing past one another like bright embers in a gale. Those speeds imply a deep gravitational well holding them in. Count the stars and gas, and the well is not deep enough. This is the classic missing mass problem in its most brutal form, because the cluster is a laboratory with many independent tracers. If Abell 2029 had only what we see, it would fly apart within a cosmic moment. Yet it remains bound, a city of matter resisting cosmic expansion locally. The cluster is not merely a collection of galaxies, but a gravitational ecosystem with rules enforced by mass. Something massive is doing the binding, and it is not luminous. A second line of evidence comes from the hot intracluster medium, the thin gas between galaxies. The gas is tenuous, far emptier than any vacuum chamber on Earth, yet it is extremely hot, heated to tens of millions of degrees by the cluster's gravity. At those temperatures it shines in X-rays, turning the cluster into a ghostly blue ember in space observatories. Its temperature and pressure profile tell us how strong gravity must be, because the gas is not free to drift. Hydrostatic balance demands that outward pressure gradients counter inward gravitational pull, and that balance can be read like a fingerprint. When astronomers model that equilibrium, the implied mass rises far above what baryons provide. This method is not perfect, because clusters can be stirred by mergers and turbulence. Even so, the broad conclusion survives different assumptions and different instruments, from early X-ray satellites to modern observatories with sharper spectral vision. The gas, in effect, is a thermometer pressed against the cluster's gravitational wall. Different methods converge on the same conclusion, and that convergence matters. Galaxy motions, X-ray gas, and later lensing all point to extra mass, even though they rely on different physics and different data pipelines. The missing mass is not a calibration error in one instrument, or a trick of one wavelength. It is a property of the universe's bookkeeping, and it shows up wherever gravity has time to organize matter. That is why Abell 2029 is such a compelling stage. Its scale amplifies the discrepancy until it becomes unavoidable. The cluster is a loud argument made out of orbits. Then comes the evidence that feels like a trick, because it uses light to map darkness. Gravitational lensing is warped space acting like a cosmic magnifying glass, except the lens is not glass at all. Mass bends spacetime, and spacetime bends the paths of photons, so the background sky is distorted by what lies in front. On screen, the idea is almost tactile, a sheet of starlight stretched over a hidden weight. Where the mass is concentrated, the sheet dips, and the distant galaxies behind it appear pulled into crescents. The universe becomes its own optical bench, with gravity as the lens maker. In strong lensing, the distortion becomes dramatic and geometric. A background galaxy can be stretched into arcs around a cluster core, bright ribbons that curve as if painted by a careful hand. Sometimes it becomes an Einstein ring, a near circle of duplicated light, wrapping the lens like a halo. The ring is not a special object, It is a special alignment. It happens when the source, lens, and observer line up closely enough that multiple light paths arrive at our telescopes. One galaxy becomes several images, and the spacing between them encodes the lens's mass. In weak lensing, the effect is subtler, but more powerful statistically. Many background galaxies are sheared slightly in the same direction, their shapes nudged away from randomness by the foreground mass. Their shapes, averaged over large samples, reveal the mass distribution of the lens, even where no arcs appear. The map that emerges does not follow the light perfectly. In a reconstruction, you can overlay galaxy positions and still find that the gravitational contours swell beyond the luminous ones. It is as if the cluster's visible city lights sit inside a much larger unlit metropolis. That mismatch is one of the chapter's core shocks, because it breaks the naive expectation that brightness tracks mass. The brightest galaxies are not always at the densest mass peaks, especially after a violent interaction. The hot gas can be offset from the gravitational center after mergers, pushed aside by ram pressure like smoke in a wind. Lensing traces the dominant mass, and it often points to something collisionless. Dark matter behaves like a component that passes through itself and through gas, interacting so weakly that it does not shock, cool, or pile up like plasma. In cluster collisions, gas can lag and compress while the mass peak keeps moving. Lensing lets us watch that separation, and it reads like a confession. The gravitational center marches on while the luminous gas, bright in X-rays, falls behind, slowed by electromagnetic interactions. The simplest interpretation is that most of the mass is in a form that does not feel that drag. So dark matter is not introduced as a fantasy ingredient, added to save a theory out of pride. It is introduced as the simplest explanation that fits multiple independent measurements, each with its own failure modes and uncertainties. Rotation curves say halos exist around galaxies, and cluster dynamics say clusters are heavier than their light. Lensing says the mass is real and spatially structured, not a mathematical mirage. The three lines of evidence do not merely agree on more mass, they agree on where that mass must be distributed. In Abell 2029, that distribution is the hidden architecture behind the visible scene. Now we connect this to IC 1101 because the giant galaxy is not floating free, it sits at the center of Abell 2029, and that center is the deepest part of the cluster's potential, the place where orbits naturally linger. The galaxy's growth is guided by the shape of that potential, and the potential is dominated by dark matter. Think of dark matter as the invisible scaffold of the cosmos, the framework that holds the luminous parts in place. In the early universe, small density ripples grow under gravity, seeded by tiny fluctuations imprinted in the infant cosmos. Dark matter clumps first because it does not couple to radiation the way normal matter does. In plain terms, it can start collapsing earlier, while ordinary matter is still pressured by light. Before atoms formed and photons decoupled, baryons were tied to radiation in a hot plasma, resisting collapse. Dark matter, largely indifferent to that radiation, began building wells before gas could settle efficiently. Those wells become halos, and halos become the addresses where galaxies form. Gas falls into the dark matter potential, heats as it converts gravitational energy into thermal motion, then cools and condenses when it can radiate energy away. Stars ignite where the gas becomes dense enough, and the visible galaxy becomes the luminous residue of a much larger dark structure. This is why the universe looks like a web when we map it at the largest scales. Halos form along filaments and meet at nodes, where gravity has gathered matter for billions of years. Clusters sit at those nodes, and they keep growing by accretion, pulling in groups and galaxies along the filaments like traffic converging on a city. Halos merge as structure grows, and that merging is hierarchical. Small halos combine into larger halos over billions of years, and the process is not gentle, even when it is slow. Each merger deepens the potential and increases the capture cross-section, making the winner more likely to win again. The biggest halos are the ones that keep winning the supply chain. They sit at intersections of filaments, where matter flows are richest and most persistent. Over cosmic time, that advantage compounds, and the central galaxy becomes a record of many arrivals. This is why the largest galaxies live in the largest halos, and why their environments feel so extreme. A deep halo pulls in more satellites and holds onto them, even when their orbits are fast and elongated. It also holds hot gas in a stable atmosphere that can strip newcomers, turning the cluster into a place where galaxies are processed. The environment becomes a machine for turning many galaxies into one central dominant. You can picture the outskirts as a slow conveyor of infalling systems, and the core as a crowded interchange where trajectories cross and energy is redistributed. IC 1101 is not just large because it formed big, but because it kept receiving material. In Abell 2029, the halo is not just large, it is cluster scale. Extending far beyond the visible core, the dark matter mass budget dominates the total by a wide margin, setting the gravitational tone for everything else. Stars are a minority component, and the hot gas is large but still not enough. The cluster's gravity is mostly the gravity of something unseen. That dominance changes the pace of violence in the core, because a deeper potential well means higher orbital speeds. Higher speeds mean encounters are more energetic, even when they do not merge cleanly, and close passes can be transformative. Stripping becomes efficient, and the debris field grows. As galaxies plunge through the core, their outer stars feel tides that stretch and peel them away, while their gas is swept back by the intracluster medium. The cluster does not need to destroy galaxies outright to reshape them. It only needs to keep pulling. Dynamical friction works harder in a dense background, and the background is mostly dark matter. A massive satellite raises a gravitational wake in the halo, a trailing overdensity that acts like a drag force. The wake pulls back and drains orbital energy, so the satellite spirals inward over time. This is the quiet mechanism that makes the center a collector, and it operates even when the sky looks serene. The cluster halo is the conveyor belt, and it never stops because gravity never turns off. Even when the central galaxy is quenched and red, the halo keeps delivering old stars. IC 1101 can keep growing without forming many new stars, simply by cannibalizing the stellar mass of arrivals. In visual terms, the galaxy's outskirts brighten not with newborn blue clusters, but with the accumulated glow of ancient populations. The growth is additive, like layers of sediment laid down by repeated floods. The same deep potential also accelerates tidal stripping in a way that blurs boundaries. As galaxies pass near the center, tides peel away their outer stars first, because those stars are least tightly bound. Those stars join streams, shells, and eventually a smooth intracluster glow, faint enough to vanish unless exposures are deep. The boundary between IC 1101 and intracluster light becomes a dynamical gradient rather than a sharp edge. With each interaction, more stars are promoted from galaxy members to cluster wanderers, orbiting the overall potential instead of one luminous core. The cluster's dark scaffold decides how easily that promotion happens. This returns us to the earlier question about IC 1101's edge, and why it is so hard to define. Some outer light is bound to the galaxy's own potential, especially where the stellar density remains high. Farther out, stars orbit the cluster more than the galaxy, and their paths are shaped by the cluster-scale halo. Dark matter decides where that handoff happens because it sets gravitational dominance with radius. The deeper and more extended the halo, the farther out stars can remain bound, at least for long times. In a shallower environment, the same stars would drift into the intracluster population more readily. So when we argue about the galaxy's size, we're also arguing about the halo. A deeper halo can keep stars bound at larger radii, and it can also keep their orbits coherent enough to sustain a vast envelope. A shallower halo would let them disperse as intracluster light, thinning the galaxy's apparent reach. The definition problem is real, but the physics underneath is still gravitational. What changes is not the law, but the bookkeeping, where we draw the line between one bound system and a larger bound system that contains it. IC 1101 sits at that ambiguous interface where galaxy and cluster overlap. Now we build the analogy that makes the dread accessible without losing the science. Imagine an invisible mountain range in complete darkness, with valleys, ridges, and a single deepest basin. You cannot see the rock, but you can see glitter thrown onto it, and the glitter collects where gravity guides it. The glitter is the stars, bright and easy to photograph, scattering light into our detectors. The mountain is the dark matter potential, massive and unseen, shaping where the glitter can settle. Where the mountain is deepest, the glitter piles up the most, and it becomes hard to tell where the pile ends. IC 1101 is glitter concentrated at the deepest point in Abell 2029. In wide-field imagery, the core glows like a pale lantern, while the outskirts fade into a mist that merges with the cluster's diffuse light. The eye wants a boundary, but the mountain does not provide one. The analogy also explains why the center is special without making it mystical. The deepest point is not chosen by beauty, it is chosen by gravity, and gravity is indifferent to what it gathers. Orbits decay toward it because energy is redistributed, and the cluster halo makes the center a sink for mass and history. Dark matter also shapes what the cluster does to gas, and gas is the fuel for future stars. Infalling galaxies carry cold gas, but the cluster's hot atmosphere strips it through ram pressure, like wind tearing fabric from a moving body. The dark halo holds that hot atmosphere in place, maintaining the pressure and temperature that make stripping effective. The halo indirectly starves satellites and keeps the core dominated by old stars. Over time, the cluster becomes a place where star formation is suppressed, not by a lack of material in the universe, but by the environment's ability to heat and remove it. The luminous population ages, reddens, and accumulates. This is where wonder turns toward unease, because the universe's main ingredient is untouchable. Most of the mass is not atoms, not planets, not stars, not us, and it does not participate in chemistry or biology. It is something that does not make light and does not care about temperature, yet it dictates where galaxies live and how they collide. We can describe it with equations and maps, but we cannot hold a sample. We can infer its distribution, but we cannot see its face, and that absence is psychologically sharp. It is the majority, and we are the minority, living as a thin, luminous frosting on a dark framework. The dread is not that dark matter is malicious, because the evidence suggests no intent at all. The dread is that it is indifferent and everywhere, shaping outcomes without ever appearing in the scene. It is the stage on which every merger in Abell 2029 plays out, and it is the reason ICR-01 had so much material to eat. It is also the reason it had so much time to keep eating, because deep potentials persist. The cluster's halo anchors the system against disruption, maintaining a stable environment where dynamical friction, stripping, and accretion can operate for billions of years. In that long patience, the monster grows. Now we tighten the connection to the central question, because this chapter is a hinge. How did ICR-01 become the largest known galaxy in the observable universe? It became large because it sits in the deepest accessible well, where the supply lines of matter converge and where orbits tend to end. That well is mostly dark matter, and it has been collecting for billions of years. The black hole can regulate gas and sculpt the core, but the halo sets the supply and the gravitational reach. The cluster environment can strip and recycle stars, but the halo sets the speeds and the frequency of damaging encounters. The outer envelope can blur into intracluster light, but the halo sets the binding and the transition radius. The invisible scaffold is the common cause, linking the small-scale story of a galaxy's outskirts to the large-scale story of a cluster's assembly. Without the scaffold, the visible narrative collapses. We should also be honest about what remains unknown, because mystery is part of the structure. We still do not know what dark matter is made of, even though we can measure its gravitational influence with growing precision. It could be a new particle, or a family of particles, or something more exotic that behaves like matter only through gravity. What we do know is how it behaves gravitationally on large scales, and that behavior is enough to build a cosmic web. Simulations that include dark matter reproduce the filamentary structure we observe, and they naturally produce massive halos at nodes. Abell 2029 is one node, and IC1101 is the luminous signature of its center. So the hidden architecture is not a footnote, it is the main plot. The universe is mostly something we cannot touch, and it shapes everything we can, from the paths of stars to the fates of galaxies. IC1101 is not just a big galaxy, it is a tracer of a far bigger dark structure. The monster's outline is drawn by invisible mass. If dark matter sets the stage, the next question is scale. How big is big in the universe, really? To answer that, we have to step back again, past clusters and halos, and confront the yardsticks themselves. If dark matter sets the stage, the next question is scale. How big is big in the universe, really? We return to the only ruler that feels real, the one our bodies trust. We start on Earth, because Terra needs a familiar floor, something with gravity underfoot and horizon we think we understand. Earth is 12,642 kilometers wide, a clean number that still breaks intuition at human speed. On a map it looks manageable, yet the curvature hides itself until you fly far enough. A jet takes hours to cross continents, and the planet still feels endless, because our senses evolved for valleys and coastlines. From orbit, the illusion collapses into a thin blue arc. The continents become stains of colour, the oceans become a dark lens, and the atmosphere becomes a fragile rim, more like a varnish than a shield. Space begins 100 kilometres up, yet the psychological distance is larger than the physical line. That boundary, the Kármán line, is partly convention, yet it marks a real shift. Above it, wings stop working, air stops behaving like air, and the sky stops being a place. The atmosphere is a thin skin, and everything we breathe is trapped inside it. Most of its mass sits in the lowest few kilometres, which means the breathable world is a shallow layer on a rocky sphere. When rockets climb, they don't just rise, they exit a system that keeps us alive. The moon is our first step outward, and it is still close enough to feel like a neighbour. It hangs there like a scar in the night, a familiar coin that never quite changes size. Yet the average distance is about 380,400 kilometres, and that gap is already a vacuum you cannot cheat. Light takes about 1.3 seconds to cross that gap, and rockets take days. The Apollo missions made that distance feel conquerable, but the historical context matters. Those flights were not routine travel, they were a peak of industrial focus, navigation discipline, and risk tolerance. Even the moon's pull is a reminder that distance still means influence. Its gravity tugs our oceans into tides, and its slow recession, centimetres per year, records energy leaking from Earth's rotation. Scale is not only about far away, it is about what can reach you. The sun is the next anchor, and it rewrites distance into something colder. 1 astronomical unit is about 150 million kilometres, a number so large we replace it with a unit name. In that conversion, the mind admits defeat, and the cosmos quietly wins. Light takes roughly 8 minutes to cross 1 astronomical unit. Those 8 minutes are not trivia. They're a built-in delay that makes the universe feel slightly out of sync. Even at noon, the sun we see is already a memory, delivered late across empty space. 8 minutes means the sun we see is always a snapshot. If the sun vanished, Earth would keep orbiting in darkness for those minutes, because gravity and light share the same speed limit. The sky would look normal, and then it would fail all at once. Mercury, Venus, Earth, and Mars look like a tight family in diagrams, but the emptiness dominates. Textbook drawings cheat by necessity, compressing billions of kilometres into a page. In reality, even inside the inner system, the average spacing is mostly vacuum. That vacuum is not nothing. It is a harsh physical environment. Solar wind streams through it, magnetic fields braid through it, and micrometeoroids cross it like unseen shrapnel. The inner planets are not neighbours in a street. They are isolated outposts. Mars is about 1.5 astronomical units from the Sun, and its distance changes with orbital geometry. Sometimes it is relatively close, sometimes it's on the far side of the Sun, and the gap becomes enormous. At closest approach, light time is a few minutes, and spacecraft still need months. Those months are not laziness, they are orbital mechanics. Efficient transfers ride elliptical paths, using the sun's gravity as the engine, because carrying enough fuel to brute force the distance is unrealistic. Even our best planning is a negotiation with physics. The asteroid belt is not a wall, it's a sparse field, and that matters. Popular images show crowded rocks, but most asteroids are separated by hundreds of thousands of kilometres. The solar system is not crowded, it is a set of islands separated by black water. Jupiter is the first giant, and it makes Earth feel like a rounding error. Jupiter's diameter is about 11 Earths across, and its mass is more than 200 Earths. Its gravity is so dominant that it shapes the architecture around it, shepherding swarms and bending trajectories. Yet Jupiter is still a dust mote on the map we are building. Its orbit sits around 5.2 astronomical units, and sunlight there is already thin. The light is still bright by human standards, but the warmth fades and the shadows feel more absolute. Saturn follows, famous for rings that look solid from far away, yet are mostly space. Up close, the rings are countless icy fragments, each on its own orbit, separated by gaps and resonances. Saturn's orbit is around 9.5 astronomical units, and light needs over an hour. That hour matters in a way our brains resist. When you send a command, you wait. When you receive data, it is already history. The outer planets teach the same lesson repeatedly. Size is not the main shock, separation is the shock. Uranus and Neptune extend that lesson into a colder register. Neptune orbits near 30 astronomical units, and the Sun becomes a bright star rather than a sky. Light takes about 4 hours to reach it, and radio messages take longer because the return trip doubles the delay. At that distance, the solar system feels less like a family and more like a fading influence. The Sun still rules with gravity, but its light is diluted across a sphere of space that keeps expanding. The warmth that defines home becomes a small local condition. Now we name the boundary that people imagine as an edge. The heliosphere is a bubble carved by solar wind, and it fades into the interstellar medium. It is not a wall, but a region where the Sun's charged particles lose their dominance. Even that bubble is not a shell you can touch, and it changes with solar activity. The solar wind varies with the Sun's magnetic cycle, swelling and shrinking the boundary like breathing. The solar system is a moving weatherfront in a larger galactic sea. This is where the Voyagers enter as our narrative anchors, because they are our farthest footsteps. Voyager 1 and Voyager 2 are not symbols, even if they became mythic. They are hardware still travelling, powered by fading plutonium heat and stubborn engineering. Voyager 1 launched in 1977, and it is now more than 160 astronomical units away. Voyager 2 is farther than 130 astronomical units, still sending thin signals home. Their golden records carry curated sounds and images, a time capsule built on the hope that distance might someday be bridged. Their speeds are tens of thousands of kilometers per hour, which feels fast until you convert it. At roughly 17 kilometers per second, Voyager 1 crosses 1 astronomical unit in months. The numbers expose the trap. Fast is a local word, and space is not local. Their radio signals take more than 20 hours to reach Earth, and that delay is our first taste. Conversation becomes impossible, because even a simple question takes nearly 2 days to complete. Control becomes prediction, an act of trust in models and patience. The Deep Space Network listens for those signals with enormous dishes, rotating across deserts and mountains. The data arrives as a whisper under cosmic noise, extracted by mathematics and persistence. Even at this scale, we're already straining to hear ourselves. Yet the Voyagers have not reached any star, and they will not for tens of thousands of years. Proxima Centauri is over 4 light-years away, and that is the nearest. The nearest is not close, it is simply the least far. A light-year is not a distance you can picture, so we translate it into time. Light crosses 1 light-year in 1 year, and Voyager would need tens of thousands. That comparison is not meant to shame the mission, it is meant to reveal the true size of the room. The solar neighbourhood is a sparse cloud of stars separated by light-years of vacuum and dust. Between them are thin gases and magnetic fields, and occasional grains moving at lethal speeds. The nearest stars are not nearby, they are simply the first islands in a dark archipelago. We can stack the planets like beads and still not touch the scale of interstellar space. The solar system is a local bubble, and the galaxy is the ocean. When you leave the heliosphere, you do not arrive somewhere else. You enter the long in-between. Now we widen again to the Milky Way, because it is our home galaxy and our next rung. The Milky Way is a barred spiral with a disk, a bulge, and a halo. In long exposure images, its arms look like painted strokes, but the structure is made of countless moving parts. Our Sun sits in the disk, about 26,000 light-years from the centre, orbiting once every 230 million years. That single orbit contains the entire age of complex life, from early animals to cities and satellites. We are not just small in space, we are brief in a galactic year. The Milky Way is about 100,000 light-years across in its bright disk, with a halo extending farther. It contains hundreds of billions of stars and probably more planets. The night sky is not a dome, it is a cross-section through a vast rotating system. The galaxy is not a flat picture, it is a layered structure. The thin disk holds young stars and gas, where new suns still ignite. The thick disk and halo hold older populations and globular clusters, relics that orbit like drifting embers. Even inside our own galaxy, distance is a kind of censorship. Dust blocks visible light across the plane, hiding the centre behind dark lanes. We infer structure through infrared, radio, and motion. By watching how stars and gas respond to gravity, the centre hosts a supermassive black hole, Sagittarius Aor, about 4 million solar masses. It is quiet now, yet it still defines the inner gravitational choreography. Stars near it whip around at astonishing speeds, tracing invisible mass like filings around a magnet. Crossing the Milky Way is beyond current technology, and the numbers are merciless. At Voyager speed, crossing 100,000 light-years would take billions of years. The galaxy is not a destination. It is an environment that outlasts any single journey we can imagine. Even at 1% of light speed, a dream far beyond today's propulsion, the crossing takes 1,000,000 years. 1,000,000 years is longer than recorded human history by orders of magnitude. It is long enough for languages to vanish, continents to reshape, and civilizations to become fossils. Modern ambition matters here because it shows the gap between engineering and the cosmos. SpaceX can land rockets and plan Mars missions, and that is real progress. Reusability changes economics, and economics changes what becomes routine, but routine still lives close to home. But Mars is a nearby shore, not the open ocean. A Mars transfer is months, with launch windows that open and close like tides. A starship to another star is generations, and a ship across the galaxy is civilizations, if it is possible at all. The Milky Way is not a single object you can traverse like a continent. It is a rotating system with differential motion, spiral arms, and a halo of dark matter. The stars do not march together, they shear and drift, and the map changes while you travel. Our galaxy is also not alone, and that is where the ladder steepens. The local group contains the Milky Way, Andromeda, and dozens of smaller galaxies. Many are faint dwarfs, held like debris in the gravity wells of their larger neighbours. Andromeda is about 2.5 million light-years away, and it is already a scale shock. Light from Andromeda left before humans built cities, and it arrives as a faint smear. When you look at it, you're looking across time as much as across space. The Milky Way and Andromeda will likely merge in several billion years, and that future is a reminder. Galaxies are not static. They are slow collisions guided by dark matter halos that interpenetrate long before the stars meet. The night sky will change, not with drama, but with inevitability. Now we place IC 1101 back into this ladder, because the earlier chapters built its case file. IC 1101 sits at the centre of Abell 2029, more than 1 billion light-years away. In images, it appears as a pale, swollen glow, surrounded by a swarm of cluster members. It is a CD galaxy with an extended envelope that dissolves into intra-cluster light, and that boundary remains a definition problem. The size depends on where you draw the line between galaxy and cluster glow. The outskirts are so faint that measurement becomes an argument between instruments and models, but even the conservative framing is enough to trigger vertigo. The Milky Way is about 100,000 light-years wide, and IC 1101's diffuse envelope may extend to about 6 million light-years. The comparison is not subtle, it is a rupture in scale. 6 million light-years is not a number, it is a sentence about time. Light needs millions of years to cross it, even in perfect emptiness. Nothing we build can compete with that, because the limit is not engineering, it is the structure of space-time itself. If you tried to cross IC 1101 at Voyager speed, the travel time becomes absurd, far longer than the age of the universe. Even at light speed, the crossing is a multi-million-year journey. The galaxy is so large that crossing it stops meaning what crossing usually means. This is scale horror, because it breaks the mind's ability to hold a whole object. A planet can be imagined as a sphere, with a surface you could walk. A solar system can be imagined as an orbit map, with paths you can trace. A galaxy already strains that ability because it is not a single surface. It is stars, gas, dust, dark matter, and time, all occupying a volume that refuses intimacy. You cannot stand anywhere and see it as a whole, because the whole is too spread out to arrive at once. IC 1101 goes further because its edge is not an edge. Its brightness profile fades into the cluster background, and the outskirts may be stars orbiting the cluster more than the galaxy. The boundary is a gradient, and gradients are where certainty dissolves. That ambiguity is not a loophole that reduces the terror, it increases it, because it suggests the monster is partly the city around it. The galaxy is a core, and the cluster is the body, an extended gravitational organism with no clean skin. We connect this to the central question, because scale is not separate from origin. How did IC 1101 become the largest known galaxy, and what does that reveal about cosmic history? The question is not only how big, but how assembled, and at what cost. The answer is not one event, and it is not one appetite. It is gravity plus dark matter plus time, operating inside a cluster that keeps delivering material to the centre. In cluster cores, galaxies fall inward, interact, and are slowly dismantled by tides that do not need intention. Earlier we promised that the halo decides the handoff between galaxy and intracluster light, and this is where it lands. The deeper the potential, the farther out stars can remain bound, at least temporarily, but repeated encounters heat those orbits, and stars become wanderers in the cluster's shared glow. So when we say IC 1101 is 6 million light-years across, we're also saying Abell 2029 is a deep, dark architecture. The galaxy's claimed size is partly a measurement of the cluster's gravitational reach. The monster's shadow is cast by the larger well it lives inside. Now we return to the solar neighbourhood to make the contrast sting. Earth is a point. Even when you zoom until continents appear, Jupiter is a point. Saturn is a point. The entire planetary system is less than a light day across, a tiny pocket of motion around one star. A light day is about 173 astronomical units, and Voyager has barely reached that scale. The Milky Way is 100,000 light-years across, and IC 1101 may be millions. The ladder is not gentle and it is not linear, because each rung changes what far even means. Each rung is a jump in both distance and meaning, because the physics changes with scale. In the solar system, gravity is dominated by one star, and orbits are predictable for long times. In the galaxy, gravity is collective, and stars respond to a distributed mass they cannot see. In a cluster core, gravity is an ecosystem, and galaxies are processed by tides, stripping, and repeated encounters. Gas can be removed, star formation can be quenched, and stellar halos can be inflated by debris. IC 1101 is the ledger where those encounters accumulate, written in faint light. The Voyagers become a moral measure here, because they represent the farthest reach of human intent. They carry records, images, and a message that assumes someone might listen. Their existence proves that we can push beyond instinct, even if the universe does not notice. But the universe does not meet us halfway. The Voyagers are still inside the sun's local influence, and they are still microscopic compared to even one spiral arm. The gap between we went far and we crossed space is the gap this chapter keeps exposing. This is not meant to humiliate exploration, it is meant to calibrate it. Our species is learning to step off one world, and the cosmos is built on million light-year architecture. Calibration is a kind of respect, because it replaces fantasy with an honest map. Now we translate IC 1101's scale into the only unit that does not negotiate: time. If light takes millions of years to cross the galaxy's envelope, then every event inside it is separated by deep delay. The far side is not just distant, it is temporally remote. A signal from one side to the other is a message to a future that may not share your species, your star, or your cluster environment. Cause and effect become stretched, and coordination becomes impossible. Even the idea of a synchronized now becomes local, a small agreement near a small star. Even the galaxy's own history becomes hard to read, because the outskirts are a graveyard of mergers and stripping. The faint halo is made of stars that once belonged to other galaxies. Their orbits remember old collisions, but the memory is smeared into a diffuse ghostly light. That returns us to the earlier narrative beats about cost. Clusters build central giants by dismantling their neighbours. The prices quench spirals, stripped gas, and stars promoted into intracluster wandering, light without a home, drifting through the cluster like ash. IC 1101 is terrifying not because it is evil, but because it is honest. It shows what gravity does when it has enough mass and enough time, and it does not care who is watching. The universe is not hostile, it is indifferent, and indifference at this scale feels like a verdict. Now we tighten the documentary's hook until it feels personal again. What if the Milky Way could fit inside a single galaxy, and still leave room for dozens more to drown in its glow? What would home mean if your entire stellar city became a small neighbourhood inside someone else's outskirts? On this ladder, that is no longer a metaphor, it is a scale comparison with consequences. It means our entire night sky is a small neighbourhood inside a much larger structure. It also means that the universe's true geography is not made of planets, or even stars. It is made of halos, clusters and the slow violence that assembles them. The vertigo is earned, and it is not optional, because the numbers are not negotiable. The mind wants a centre, but the universe offers only local centres, nested inside larger wells. We end this chapter by turning that dread into a doorway, because the next stakes are not only size. If space is this vast, what about what's inside it? What kinds of worlds can exist when the universe has so many places to try and so much time to iterate? The Milky Way holds hundreds of billions of stars, and many of them have planets. Beyond it, other galaxies hold trillions more, and the inventory becomes uncountable. With that many chances, rarity becomes complicated, and the word normal starts to lose meaning. The question shifts from how far to what kind: planets, exoplanets, and worlds shaped by radiation, tides, and chemistry we barely understand. Transition. If the universe can build a galaxy like IC 1101, then it can also build environments that are stranger and more dangerous than our instincts allow. Next, we move from scale to content, and we ask what kinds of worlds exist inside this vast, indifferent architecture. If space is this vast, what about what's inside it? Planets, exoplanets, and the strange, dangerous worlds that orbit other stars. Exoplanets keep the story human, because they turn distant scale into possible ground beneath imagined feet. They also sharpen the dread because the universe builds worlds without caring who could live there, or whether anyone can. For most of history, planets beyond the solar system were philosophy, not data, and the night sky kept its secrets. Then, in the late 20th century, precision instruments made a quiet revolution possible. The first strong detections in the 1990s did not arrive as pictures, but as numbers that refused to go away. Astronomers do not usually see exoplanets directly, because stars drown them in glare and distance erases detail. Instead, they watch for tiny betrayals in starlight and motion, and they turn those clues into worlds. A planet becomes a measurable disturbance, small, periodic, and stubbornly repeatable. The transit method is the cleanest betrayal, because a planet can cross its star from our line of sight. The star dims by a fraction, on a schedule, and that repeating dip becomes a planetary fingerprint. On a plot, it looks like a heartbeat that briefly falters, then resumes as if nothing happened. Depth tells us the planet's size relative to the star, and timing tells us the orbit. Multiple transits lock in the period, and the light curve shape hints at geometry. The steepness of the dip's edges can even suggest how fast the planet moves across the stellar disk. In careful data, the transit is not just a dip, but a silhouette with physics inside it. Limb darkening makes the star's edge dimmer than its center, so the same planet blocks different amounts of light. That subtle curvature helps constrain the star's properties, which then calibrate the planet's radius. Transits demand alignment, so they miss many systems by pure chance and by simple geometry. That bias matters, because it skews the sensors toward close-in planets with frequent crossings. The method prefers tight orbits, where the probability of alignment is higher and the signal repeats quickly. False positives also stalk the transit method, and the pipeline must be skeptical by design. An eclipsing binary star can mimic a planet, and background stars can contaminate the aperture. That is why astronomers demand consistent periods, consistent depths, and follow-up checks from independent instruments. The radial velocity method watches the star instead of the planet, and it treats gravity as a metronome. A planet's mass tugs the star into a small wobble, and spectral lines shift as the star moves. The shift is tiny, but it is coherent, cycling with the planet's orbit. Those Doppler shifts reveal a minimum planet mass and an orbital period, because inclination can hide the full amplitude. Combine wobble with transits, and you can measure density, which separates gas giants from rocky worlds. Density is where a dot on a chart becomes a physical category: puffy, icy, or iron-rich. Radial velocity is also a war against noise, and the noise is often the star itself. Star spots rotate in and out of view, granulation boils on the surface, and magnetic cycles change line shapes. To pull out a planet, astronomers model stellar activity and demand signals that persist across seasons and instruments. These methods are not tricks. They are precision metrology at cosmic distance, built on stable clocks and calibrated spectra. They turn photons into statistics, then statistics into physical objects with mass, radius, and heat. The mathematics is cold, Yet the result is intimate, another world inferred from a star's slight hesitation. NASA missions expanded the census by making those measurements routine and systematic, rather than heroic one-offs. Kepler stared at one field for years, and it converted rare detections into a population study. Its camera became a patient watcher, measuring brightness with the discipline of a laboratory instrument. Kepler's result was not one famous planet, but a space fact about abundance that changed the conversation. Planets are common, and small planets are especially common, even when they are hard to confirm. The galaxy is not sprinkled with worlds, it is saturated with them. Kepler also revealed a surprise category that our solar system does not contain. Sub-Neptunes and super-Earths appear everywhere in the data, sitting between Earth and Neptune in size. Their existence raises a quiet question. Why did our system skip that common outcome? TESS shifted the strategy toward nearby bright stars, where follow-up is easier and uncertainties shrink. That choice trades depth for accessibility, and it builds a catalogue suited for atmosphere studies. Nearby stars are brighter, so the same fractional dip becomes a cleaner measurement with more photons. CHEOPS, JWST, and ground spectrographs refine the same pipeline, adding layers of confirmation and interpretation. The Discovery machine is now stacked, with survey missions feeding characterization missions. A candidate becomes a confirmed planet, then a target, then a spectrum with chemical hints. This is why NASA Discovery headlines keep arriving, even when nothing is photographed in the familiar sense. The discoveries are real, because the methods are redundant and the signals repeat. The universe is not handing us postcards, it is handing us consistent patterns that physics can only explain one way. Once you accept that planets are everywhere, the next question becomes unsettling and oddly personal. What kinds of planets does nature prefer, and how many of them are hostile by default? If Earth is it rare because it is special, or because we are biased by what we can survive? We start with the ultra-hot Jupiters, because they are the easiest to find and the hardest to imagine. They are gas giants parked so close to their stars that years last days. In some cases, the planet skims above the stellar atmosphere, as if it is almost falling in. Their atmospheres can reach thousands of degrees, hot enough for exotic chemistry and broken molecules. Some show metal vapours and violent winds, and their skies behave more like furnaces than weather. At those temperatures, even rock-forming elements can exist as gas, then condense elsewhere like alien rain. Many are tidally locked, with one face always toward the star, because gravity has erased their spin mismatch. That creates a permanent day side and a permanent night side, and the temperature contrast can be extreme. The Terminator line becomes a moving frontier of physics, not a gentle sunset. Heat redistribution becomes a planetary survival problem, driven by supersonic jets that try to equalize the imbalance. In some models, clouds can form on the night side and evaporate as they cross into daylight. The atmosphere becomes a conveyor belt carrying heat, chemistry, and condensed particles across hemispheres. Some ultra-hot Jupiters may also be slowly evaporating under intense radiation, leaving comet-like tails of gas. The star's ultraviolet light can heat the upper atmosphere until it escapes the planet's gravity. Over time, mass loss can reshape the planet, turning a giant into something smaller and stranger. These are not horror stories. They are stable outcomes of gravity and radiation, written into equations we trust. A planet can exist for billions of years in conditions that would destroy biology we recognize. Stability does not mean comfort, and longevity does not imply habitability. Some rocky planets push the same logic into a harsher register, where the surface itself becomes unstable. A close-in super-Earth can be a lava world, with molten surfaces and thin vapor atmospheres. The ground is not ground at all, but a glowing ocean of magma under a sky of rock vapor. On such worlds, the concept of an ocean becomes a different phase diagram, governed by pressure and temperature rather than familiar coastlines. Water can be steam, or it can be absent, and the surface can recycle through magma instead. Even the idea of a shoreline becomes meaningless when the crust is temporary. Then there are planets around red dwarfs, the most common stars in the galaxy, and the ones most likely to host nearby worlds. Their habitable zones are close in, which makes tidal locking likely and stellar activity unavoidable. A planet can sit in the right temperature range, yet still live under a violent sky. A flare-active M-dwarf can bathe a planet in ultraviolet and particle storms, especially during the star's long turbulent youth. If the planet lacks a strong magnetic field and thick atmosphere, the surface can be stripped and sterilized. The same star that provides warmth can also provide relentless erosion. Some worlds may keep atmospheres through chemistry, volcanism, or sheer gravity, rebuilding what is lost over time. Others may become bare rocks because the star's youth is violent and long-lived. The difference may hinge on deep interiors, how much gas is outgassed, and how long the planet can keep recycling it. We also find planets in compact multi-planet systems, packed closer than Mercury's orbit, where stability is a delicate choreography. Their gravitational interactions can pump eccentricities, drive tides, and heat interiors into instability. In such systems, a small change can cascade, shifting resonances and altering climates over geological time. Tides can be a heat source like a hidden engine, as on Io in our system, where Jupiter needs the Moon's interior. On an exoplanet, that engine can turn a potentially temperate world into a volcanic nightmare. The energy comes from orbit and gravity, not sunlight, and it can persist as long as the dance continues. Rogue planets remove the star entirely, and they widen the definition of a world beyond the comforting idea of a solar system. They drift through interstellar space, ejected by early chaos, or disrupted by passing stars. In the dark, they are almost invisible, yet they may be numerous, ghost worlds between the lights. Without sunlight, a rogue planet is not automatically dead, only different, and the distinction matters. A thick atmosphere or internal heat could keep subsurface oceans, but the energy budget is tight. Radioactive decay, residual formation heat, and tidal flexing from moons become the only candles left. Rogues are also reminders of how often systems break, even when they begin with orderly disks. Planet formation is not a clean assembly line, and many worlds are lost to the dark between stars. If our own system looks calm now, it may be because the chaos has already finished its work. The phrase horrifying planets works best when it stays scientific, because the true shock is impersonal. The horror is not monsters, it is physics that makes hostile environments common and stable. When we say horrifying, we are really describing how indifferent the universe is to our preferred conditions. Now we bring the giant galaxy back into the frame, because environment shapes what survives and what gets erased. In a cluster core, stars are older, orbits are faster, and interactions are frequent. The sky in such a region would look crowded, bright with neighbouring suns that never quite feel far away. Dense regions increase the rate of close passes between stars and between planetary systems, even when direct collisions remain rare. Even distant gravitational nudges can destabilise long-term orbits, especially for outer planets and comet reservoirs. Over millions of years, small perturbations accumulate, and stability becomes a probability rather than a promise. A passing star can perturb an outer comet cloud, sending impacts inward for millions of years like a delayed echo. In a crowded neighbourhood, those perturbations can be more frequent and less predictable. A planet may endure long, quiet eras, then face a sustained bombardment that reshapes surfaces and biospheres. The intracluster environment also changes radiation backgrounds in subtle ways that are easy to overlook. More old stars can mean more supernova remnants in the past, and more compact objects over time. The cluster becomes a museum of stellar evolution, and museums contain relics that still radiate. Energetic events are not evenly distributed across a cluster, because gravity funnels matter toward the centre. The centre is where gas piles up, where black holes feed, and where outbursts can reshape conditions across large volumes. In visuals, it is a slow whirlpool of light and hot gas, threaded by shock fronts. Active galactic nuclei episodes are the sharpest example of that power, and they scale with the appetite of the central black hole. When a central black hole accretes, it can launch jets and flood the region with high-energy radiation. The jets carve cavities in the hot gas, like invisible drills that leave bubbles visible in X-rays. We have already seen how AGN feedback solves the cooling flow problem by heating cluster gas and preventing runaway star formation. The same outburst can also create sterilization zones for nearby planetary systems. The mechanism is not mystical, it is energy deposition, photon by photon, particle by particle. Radiation does not need to hit a planet directly to matter, because atmospheres are chemical machines exposed to the sky. It can erode atmospheres, break molecules, and change climate chemistry, especially on worlds already near the edge. A small shift in ozone-like shielding or greenhouse balance can tip a marginal world into collapse. The danger is strongest near the nucleus, but the influence can extend far through jets and shocks that propagate through the cluster medium. In a seedy galaxy like IC 1, the central engine is not a footnote. It is a historical actor, with episodes that may have rewritten the conditions of entire stellar neighbourhoods. If IC 1's black hole experienced repeated feeding and mergers, its past may include luminous phases that are now long extinguished. Those phases could have been brief, but brief is enough at high intensity. In astrophysics, 1,000,000 years can be a flash, yet still be long enough to strip atmospheres. A hard X-ray and gamma-ray environment can damage ozone-like shields and expose surfaces, even if the planet is otherwise well placed. A planet can be habitable for eons, then lose that status during one energetic era. The unsettling part is the timing. Habitability can end without warning, triggered by distant accretion. Cluster centers also host hot X-ray gas, and that background matters for atmospheres and magnetospheres over long times. It is thin, but it signals a high-energy environment shaped by deep gravitational wells. The gas glows because it is tens of millions of degrees, and its particles carry the memory of shocks and mergers. In the outskirts of calmer galaxies, cold gas clouds can form stars and planets gently, with fewer interruptions. Near a cluster center, ram pressure and heating reduce those calm nurseries over time. The cluster medium can strip gas from galaxies like wind-stripping leaves, leaving fewer raw materials for new, quiet systems. That does not mean planets cannot form there, but it changes the odds and changes the timeline. The supply of cold gas is stripped, star formation is quenched, and the population shifts toward older systems. Older systems can still host planets, yet their histories include more radiation exposure and more gravitational harassment. Older systems can still host planets, but they carry long histories of irradiation and dynamical disturbance that accumulate like scars. Habitability becomes a moving target, not a fixed label, and not a guarantee that persists once achieved. The question becomes not only where life could start, but where it could keep going. This is where the documentary's scale horror becomes biological scale horror, and the bridge between them is environment. A giant galaxy is not only big, it sits in a city where the rules are harsher. The same density that builds grandeur also raises the background risk for every orbiting world. Now we contrast with our own solar system, because familiarity is the control sample, and because it anchors the stakes. We live in a relatively quiet spiral disk region, far from the Milky Way's central black hole. Our night sky is not empty, but it is not crowded, and that spacing is a kind of protection. Jupiter and Saturn are not just scenery, they are gravitational architects whose influence reaches far beyond their visible disks. They sculpt the asteroid belt, shape comet reservoirs, and influence impact rates on the inner planets. Their mass creates resonances, mathematical rhythms, that herd debris into gaps, clusters, and long-lived pathways. They can act as shields by ejecting or capturing potential impactors, but they can also redirect them toward the inner system. The same gravity that protects can also deliver danger, depending on geometry and timing. In a different arrangement, a Jupiter-like planet could increase impacts, turning a habitable zone into a shooting gallery. Jupiter's resonances carve gaps and concentrate debris, and that structure affects Earth's long-term risk in measurable ways. The solar system's stability is a negotiated outcome, not a guarantee, and it depends on orbital spacing and early history. Even small changes in giant planet migration could have rewritten the inner planet's fates. Mars shows how habitability can fail without needing a single catastrophe, and that makes it his sobering neighbour. It likely lost much of its atmosphere, its surface water became unstable, and its climate shifted toward cold dryness. The evidence is written in dried river valleys, mineral deposits, and ancient lake beds that now sit under thin air. Its smaller mass and weaker magnetic protection made it more vulnerable to solar wind stripping over billions of years. Mars is a case study in fragility, even within a relatively calm stellar neighbourhood. It reminds us that being in the right place is not enough if you cannot hold on to air and water. Earth shows the opposite, but only temporarily and only locally, because stability is an active process. Plate tectonics, a magnetic field, and a thick atmosphere help stabilise climate, but none are permanent promises. Even Earth's carbon cycle is a balancing act, and balance can fail when inputs change. Earth's history includes mass extinctions, impact events, and climate swings that reshaped life repeatedly. Habitability is not a binary state. It is a range maintained against constant physical pressure. The planet is habitable now, yet it has not always been equally kind, and it will not always remain so. When we look at exoplanets, we are looking for those stabilizing feedbacks at a distance, using light as our only probe. We infer atmospheres through transmission spectra, thermal emission, and phase curves. In a transmission spectrum, starlight filters through the planet's limb, and molecules leave faint absorption fingerprints. We look for water signatures, carbon chemistry, and temperature constraints, but interpretation is hard and often contested. Clouds can mimic signals, stellar activity can contaminate data, and models can disagree. Even the star's spectrum can imprint features that masquerade as planetary atmosphere, so every claim must be tested against alternatives. Even so, the trend is clear and it is unsettling, because extremes dominate what we can easily detect. The universe produces many more extreme worlds than Earth-like ones, at least in the samples we can detect easily. The catalogue reads like a list of exceptions, yet those exceptions may be the norm. Detection bias is part of that story, because hot close-in planets are overrepresented in both transit and radial velocity surveys. But the deeper truth remains that Earth is not the default outcome of planet formation. The ingredients are common, yet the final recipe depends on timing, migration, impacts, and long-term stability. Now we place this back under IC 1101's shadow, because the central question is still driving the chapter forward. How did IC 1101 become the largest known galaxy, and what does that reveal? Size is not just a number here, it is a signature of repeated mergers, long accretion, and an environment that rewards accumulation. A cluster core that can assemble a 6 million light-year envelope can also erase gentle conditions, simply by being crowded and energetic. The same interactions that build the giant can destabilize planetary systems and starve future formation. Growth and hazard are not separate stories. They are the same physics viewed at different scales. The boundary problem returns here as more than a measurement argument, because it changes what we mean by inside. If IC 1101's outskirts blend into intra-cluster light, then inside the galaxy may include stars on cluster-like orbits. Those stars are bound to the cluster's potential as much as to the galaxy's luminous core. Those stars live in a shared gravitational ecosystem, with higher encounter rates and a different radiation history than a quiet spiral disk. The galaxy's size becomes a proxy for how deep and violent the environment is. When the envelope is enormous, it implies a long record of interactions that also disturb smaller systems. This is why exoplanets belong in this chapter, even though IC 1101 is far away and beyond direct planetary study. They translate structure into stakes, because worlds are where physics becomes lived experience. A halo is abstract until you imagine a planet trying to keep an atmosphere inside it. We can imagine standing on a planet under a different sky, but we cannot imagine controlling the cluster that surrounds it. The cluster decides the background conditions and planets adapt or fail. The question becomes hauntingly practical. What does home mean when the neighbourhood itself is unstable? The ominous tone is not speculation, it is extrapolation from known mechanisms that appear across astrophysics. Radiation, tides, impacts, and orbital chaos are universal, and dense environments amplify them. If those mechanisms operate here, they operate there, and the difference is often only intensity and frequency. Still, the story is not that life is impossible in big galaxies or clusters, because possibility is stubborn. The story is that the safe zones may be rarer, more temporary, and more dependent on local luck. A world might be safe for 1 billion years, then be pushed into danger by a passing star or a nuclear outburst. A quiet star, a stable orbit, a protective atmosphere, and time without sterilizing events. Those are the requirements that keep repeating. Those requirements are not romantic, they are constraints imposed by astrophysics. They're also a reminder that habitability is a process, not a trophy. As we approach the climax, IC 1101 becomes more than a record holder, and more than a curiosity on a chart. It becomes a clue about how the universe builds structure, and about the limits that structure imposes. The largest galaxies are not merely large, they are histories made visible. If gravity plus dark matter plus time can build a galaxy this large, it can also build histories this violent, with repeated shocks and rearrangements. The same process that creates vast halos can create long eras of hazard. The question is not whether danger exists, but how often it sweeps through the places where worlds try to persist. Transition. IC 1101 isn't just a big galaxy. It is evidence that the universe's largest cities are built by accumulation, and that accumulation has consequences for every possible world inside. From here, we turn from cataloguing worlds to reading the architecture that contains them, because the container shapes the contents. We ask what IC 1101 and Abell 2029 imply about cosmic growth, boundaries, and the ultimate scale of risk. And we ask quietly what it means that the universe can be so good at making worlds, and so indifferent to keeping them safe. IC 1101 sits in our story like a record carved into fog, an immense shape implied by faint light, not by sharp edges. We call it the biggest known galaxy, then we remember how little of it we truly see. In deep images, the core is obvious, but the outskirts arrive as a whisper. The more we stare, the more the boundary becomes an argument. The central question returns with sharper teeth, because it is really two questions braided together. How did IC 1101 become the largest known galaxy? And what does that reveal about cosmic history? The first part asks about growth, mergers, and environment, while the second asks whether our categories survive contact with data. Known is the first trap, and it hides inside the word like a concealed blade. It means measured by instruments with limits, interpreted by models with assumptions, and compared across a universe that is changing. It also means known by a particular pipeline, where choices about masking, sky subtraction, and calibration quietly decide what counts as real. Galaxy is the second trap, because the sky does not label objects for us. A galaxy has stars and dark matter, but its edge can dissolve into a cluster's shared light. In a rich cluster core, the gravitational landscape is communal, and the stars do not always respect the borders we draw. Biggest is the third trap, and it sounds absolute even when it is not. In cosmology, it depends on definitions, thresholds, and the meaning of bound structure. Are we ranking by diameter, by stellar mass, by halo mass, or by the faintest detectable contour in a particular bandpass? We have been using a headline number, roughly millions of light years, for the faint envelope, because it is dramatic and easy to repeat. Now we confront what that number is really claiming and what it quietly ignores. It is not a tape measure fact, but a statement about photons, noise, and conventions. A bright disk has a clear boundary because the light drops quickly and the background can be estimated with confidence. A seedy galaxy does not end cleanly because its halo fades into intracluster light. The outer profile can look like a slow exhale, where every additional hour of exposure reveals a little more structure. Intracluster light is not a decoration, and it is not merely glow in the poetic sense. It is a population of stars stripped from galaxies, orbiting the cluster potential more than any single galaxy. Those stars can come from tidal tails, shredded dwarf galaxies, and the outskirts of larger galaxies that were peeled away over repeated passages. So the first definition problem becomes unavoidable, and it is as much philosophical as it is technical. Are we measuring IC 1101's stellar halo, or are we measuring Abell 2029's intracluster glow? In the center of a cluster, the two can overlap so thoroughly that separation becomes a matter of statistical inference. Astronomers try to separate them with surface brightness profiles, because light still carries a memory of structure. They fit a core and an extended component, then ask where the profile changes slope. In practice, this means comparing how quickly brightness declines with radius, and whether a second, shallower component dominates at large distances. That break can mark a transition in stellar orbits, where stars stop behaving like a galaxy halo and start behaving like a cluster population. It can also be an artifact of background subtraction, scattered light, or an assumed model shape. Even the choice of fitting function, Sersic de Vaucouleurs or multi-component hybrids, can shift the inferred radius. At 1 billion light-years, the outskirts are the hardest part because the signal is thin and the sky is loud. The light is spread over a large area, and it competes with sky glow and detector systematics. A tiny error in flat fielding or a faint gradient across the detector can masquerade as a halo or erase one. Surface brightness dimming makes the problem worse with distance, and the mathematics is unforgiving. The universe stretches light and reduces apparent brightness steeply, so faint halos vanish first. In simple terms, the same physical halo becomes harder to see not because it shrinks, but because it fades into the background faster than intuition expects. That means size measurements are not just about resolution, where sharper images reveal finer details. They're about whether the outermost photons rise above noise at all. When the outskirts sit only a fraction of a percent above the sky, the edge becomes a confidence interval. Selection effects follow like a shadow, and they shape our catalogues before we ever interpret them. We find galaxies whose bright parts are easy, and we miss giants whose light is distributed too thinly. A compact galaxy announces itself, while a diffuse one can hide in plain sight, especially in crowded cluster fields. Even when a halo exists, surveys can clip it away without meaning to, and sometimes without noticing. Pipelines may subtract it as background, because the algorithm assumes the sky is flat. The very tools designed to remove gradients can treat a real, extended halo as an unwanted artifact. The biggest list is therefore partly a list of what survives processing, and that is not a comfortable thought. It is an inventory shaped by human choices as much as by nature. When we rank galaxies, we are also ranking our methods, our exposures, and our tolerance for uncertainty. This is why the record feels unstable, like a crown balanced on mist. IC 1101 may be enormous, but its claim depends on how we define the edge. The galaxy does not change when we change our definition, but our story about it does. One approach defines size by an isophote, a fixed surface brightness contour that traces where light falls to a chosen level. Another uses an effective radius, enclosing half the total light. Both methods sound objective, yet each one smuggles in assumptions about what total means when the outskirts are barely measurable. Both methods hide a problem that grows sharper the deeper we look. Total light is uncertain when the outskirts are uncertain, and a contour depends on exposure depth and calibration. If the sky subtraction is off by a small amount, the inferred total luminosity can swing, and the effective radius can follow. A deeper image pushes the contour outward, and the effect can be dramatic for CD envelopes. The same galaxy can grow on paper without gaining a single star. The record can shift not because the universe changed, but because our threshold moved. Another approach defines size by dynamics, because gravity is harder to fool than light. If stars are gravitationally bound to the galaxy, their orbits should reflect the galaxy's potential. In principle, velocities can reveal whether the outer population is a coherent halo or a cluster-wide swarm. But in a cluster core, the potential is shared, and the situation becomes subtle. Stars can be loosely bound, heated by encounters, and gradually promoted into cluster-wide orbits. Over billions of years, repeated interactions can blur the kinematic signature, turning a crisp boundary into a transition zone. So, bound to IC 1101 becomes a probability, not a binary, and that is where the discomfort lives. The boundary is a handoff region where the cluster starts to win. Even if a star is near the galaxy in projection, its true orbit may belong to the cluster's deeper well. This returns to a promise from earlier chapters, where the cluster itself loomed like an unseen engine. The cluster's dark matter-dominated potential may be the real architect of the outer envelope. In that view, IC 1101 is not simply a galaxy with a large halo, but a central condensation inside a larger gravitational basin. If Abell 2029's halo is deep enough, it can hold stars at huge radii, and it can do so for cosmic timescales. Those stars may still be counted as IC 1101, depending on convention. The naming becomes a choice about ownership. Does the central galaxy own the light, or does the cluster? That convention is not trivial, because it changes the inferred merger history and the mass profile we reconstruct. It changes the story we tell about how giants form. If we attribute more light to the galaxy, we imply more accretion and more growth in the galaxy itself, rather than in the cluster's diffuse component. If the outskirts are mostly intracluster light, then IC 1101 is a core embedded in a larger stellar sea. If they are bound, it is a true monster. Either way, the cost is written in debris, because diffuse light is rarely born gently. The halo and intracluster light are made from disrupted galaxies, stripped by tides and repeated encounters that do not leave clean survivors. In a cluster center, tidal forces can stretch a smaller galaxy into streams, then disperse those streams into a smooth glow. What looks serene in an image can be the graveyard of countless orbits. The measurement biases do not end at the optical sky, because clusters announce themselves across the spectrum. X-ray gas modelling assumes hydrostatic equilibrium, yet mergers and turbulence can break it. If the hot gas is sloshing, stirred, or supported by non-thermal pressure, the inferred mass can be biased. Weak lensing maps mass more directly, but it is not effortless truth. It averages over large scales and requires careful shape calibration. Small systematic errors in galaxy shapes, redshift estimates, or point spread function modelling can shift mass estimates and the radii we associate with bound structure. Even spectroscopy has limits, and the limits are practical as much as physical. Measuring stellar velocities in the faint outskirts is slow, and sample selection can bias which stars we track. We often rely on bright traces, which may not represent the full population, especially if accreted components have different kinematics. So the record holder status is not a trophy, and it never was. It is a hypothesis under constant revision, held up by the best data we can currently extract. The more extreme the claim, the more it depends on the faintest, most fragile measurements. Now the tension deepens, because the problem is not confined to one cluster at one distance. If our methods struggle nearby, what happens when we try to compare galaxies across cosmic time? We want a universal ranking, but the universe refuses to stay still while we measure it. Looking far away means looking back in time, and the sky becomes a layered archive. The light from distant galaxies left when the universe was younger and denser. In that era, gas fractions were higher, star formation was more intense, and mergers were more frequent, which changes what typical growth even means. That complicates biggest in a fundamental way, because the competition is not fair across epochs. A galaxy at redshift 2 is not competing in the same environment as a galaxy today. It lives in a universe with different average densities, different accretion rates, and different times available for slow halo building. The universe expands while light travels, and the geometry plays tricks on intuition. Physical sizes and angular sizes do not scale intuitively, and surface brightness dimming punishes extended halos. A distant CD envelope can be present and massive, yet effectively invisible, because its light is diluted across the detector and across time. We also face progenitor bias, which sounds technical but describes a simple trap. The galaxies we see at early times are not the same objects we see nearby, because growth and merging reshuffle identities. When we compare a compact high redshift galaxy to a sprawling low redshift giant, we may be comparing an ancestor to a descendant's environment, not to the descendant itself. A galaxy can double in mass through minor mergers, then puff up in size as accreted stars settle at large radii. Another can quench early, remain compact, and later be swallowed. The winners of the biggest race can change depending on which growth path dominates in a particular cluster. So biggest can mean biggest now, biggest at formation, or biggest at a fixed stellar mass. Each choice answers a different question, and each question implies a different physics. Are we probing early dissipative collapse, late dry merging, or the slow accumulation of stripped stars into a diffuse envelope? The most honest comparison uses a consistent definition, even if it is imperfect. Yet consistent definitions can still hide physics, because the outskirts are built late and are faint. When we standardize our measurement, we may also standardize away the very features that reveal how the system assembled. This is where IC 1101 becomes a stress test, because it pushes every method into its weak regime. Its extreme halo forces us to admit that galaxy growth is not confined to bright inner regions. The outskirts, not the core, may carry the clearest record of minor accretion and tidal processing. The outskirts are the archive of minor accretion, written in diffuse light and subtle gradients. They are also the part most likely to be missed in distant surveys. If we cannot see the archive, we may misread the history, concluding that galaxies were smaller simply because their faint envelopes were beyond detection. So the deep universe could contain giants we have not recognized, and that possibility is not speculative fluff. They might look ordinary in shallow images because their halos are invisible. A central galaxy could present a bright, compact body, while its true scale lives in light that never rises above the survey's sky model. We may already have misclassified some, and the error would be quiet. A central galaxy could be labelled modest, while its diffuse envelope is quietly merged into the background model. In crowded fields where many galaxies overlap, deblending algorithms can also assign diffuse light to the wrong neighbours. Even closer to home, the same risk exists, and it has a history. Low surface brightness galaxies can evade detection, and their true sizes can be underestimated. Astronomy has repeatedly expanded its census when detectors improved, from photographic plates to CCDs to modern wide-field cameras that can hold the sky steady. The universe is not only full of objects, it is full of objects that are hard to count. Their light is spread thin, and thin light is where our confidence breaks first. When we say we know, we often mean we know above a threshold, and the threshold is a human choice. Now we widen the frame beyond galaxies, because the word biggest invites a dangerous misunderstanding. Galaxies live inside larger structures, and those structures have their own definitions and their own ambiguities. If we do not separate categories, we end up comparing apples to continents. Clusters, superclusters, filaments, and walls are the scaffolding of the cosmic web, traced by galaxies like beads on invisible threads. Some of these structures are larger than any galaxy by orders of magnitude, yet they are not the same kind of object, and they do not share one fate. A cluster like Abell 2029 is gravitationally bound, and that binding is the key distinction. Its galaxies orbit a common dark matter halo, and the system can remain coherent for billions of years. The hot intracluster gas shines in X-rays, filling the gravitational well like a luminous atmosphere, and it marks the depth of the potential. A supercluster is often not bound as a whole, even if it looks like a single structure on a map. It can be a pattern in the cosmic web, a region of higher density that is still expanding. Parts of it may collapse into clusters, while the larger configuration continues to stretch with the universe. Filaments can stretch for hundreds of millions of light-years, and they are real overdensities in the dark matter distribution. They are not necessarily objects that will collapse into one unit. They are conduits, channels along which matter flows, and their edges are statistical, not physical. So we must separate size from binding, because the universe offers both in abundance. The cosmic web is huge, yet much of it is not a single gravitational organism. When we call something the largest, we should ask whether it is a coherent entity or a connected pattern. This distinction matters for the story's fear, because bound systems can trap matter and build monsters. An unbound structure is a map of initial conditions, a fossil of early density fluctuations stretched into the present. One is a gravitational engine, while the other is a cosmic fingerprint. When people hear larger structure, they imagine a single thing, like a continent in space. Cosmology often gives us connectedness without cohesion. The web can be continuous, yet not destined to become one object, and that subtlety is where misunderstandings breed. IC 1101 sits at a node where filaments feed clusters over time, and that location matters. Its growth is tied to that network, even if the network itself is not bound. The node is where orbits intersect, where infalling galaxies lose energy through dynamical friction, and where stripping becomes routine. This is also where the danger-filled history becomes clearer, because the web is not gentle at its intersections. The web funnels galaxies into dense regions where mergers and stripping become routine. Each infall brings new stars, new dark matter substructure, and new opportunities for the cluster to shred and redistribute them. The same cosmic architecture that builds habitable worlds also builds collision zones, and the contrast is unsettling. It is not malicious, but it is efficient. Gravity does not care whether it assembles a spiral disk or a diffuse halo of debris, and it will do both if given time. Now we return to the record itself, because the narrative demands an answer even if the universe refuses one. Is IC 1101 truly the biggest galaxy, or the biggest we can currently certify? The difference between those statements is the difference between nature's extremes and our observational reach. There are competitors and caveats, and the list shifts with every deeper survey. Some massive CD galaxies have comparable halos, and their measured sizes shift with depth and methodology. A galaxy that looks smaller in one dataset can rival IC 1101 in another, simply because the outermost light was measured more carefully. There are also objects that blur categories, and they blur them precisely where our definitions are weakest. Brightest cluster galaxies can be inseparable from intracluster light, making galaxy size a negotiated boundary. In some clusters, the diffuse component is so prominent that the central galaxy feels less like an island and more like a peninsula, and there are structures that challenge the word galaxy entirely, without leaving the territory we have been discussing. Fossil groups, merging cluster cores, and extended stellar envelopes can mimic single giants. In these cases, what appears to be one object may be a temporary configuration, caught mid-assembly. So the honest statement becomes narrower, and that narrowing is a kind of intellectual discipline. IC1101 is among the largest known central galaxies in a massive bound cluster with an extreme diffuse envelope. It sounds less cinematic, yet it is more unsettling, because it admits that our categories are under strain. It means the universe can build systems that defeat our definitions, and it can do so without breaking any laws. The uncertainty is not failure, it is the edge of knowledge, where measurement becomes philosophy backed by data. When the signal is faint and the stakes are high, even a number becomes a debate. Now we ask what would settle the case, or at least tighten the argument. What observations could separate halo from intracluster light and confirm what is bound? The answer is not one instrument, but a convergence of methods that fail in different ways. Deep imaging is the first requirement, but not just deeper in the naive sense of longer exposure. It must control scattered light, flat field errors, and background gradients with ruthless care. Bright stars outside the field can throw ghostly reflections across the detector, and those reflections can mimic the very halos we seek. Wide-field cameras help, because the halo is large on the sky and demands context. If the field is too small, the halo fills it, and the sky estimate becomes contaminated. The image then subtracts away the galaxy itself, leaving a smaller, cleaner-looking object that is simply an artifact of limited framing. Space telescopes help because they avoid atmospheric glow and the subtle variability of airglow lines. Yet they have their own systematics, including stray light and detector artifacts. Even in space, calibration is a battle against tiny effects that accumulate when you chase signals near the noise floor. Kinematics are the second requirement, because motion can distinguish populations that light alone confuses. If we can measure velocities of stars, globular clusters, and planetary nebulae at large radii, we can map binding. Each tracer is like a buoy on a dark ocean, marking the flow of an invisible gravitational current. A bound halo should show a velocity distribution tied to the galaxy, with patterns that reflect its mass profile. Intracluster stars should track the cluster potential and show different dispersion patterns. In practice, we look for changes in velocity dispersion and rotation signatures as we move outward, searching for the point where the cluster's influence dominates. Globular clusters become tracers because they are bright and numerous, and because they can survive violent environments. Their spatial distribution and motions can reveal where the galaxy's influence fades. If their orbits become more random and more cluster-like with radius, the transition from halo to intracluster population becomes harder to deny. Gravitational lensing is the third requirement because it measures mass whether it shines or not. Weak lensing can map the dark matter halo of Abell 2029 and show how mass extends beyond the light. The subtle stretching of background galaxies becomes a statistical imprint of the cluster's gravitational field. Better lensing maps reduce ambiguity, especially when combined with strong lensing constraints near the core. If the mass profile demands a large bound region around the central galaxy, the halo interpretation gains strength. If the mass is clearly dominated by the cluster at radii where the light is still attributed to IC1101, the intracluster interpretation becomes more plausible. Simulations are the fourth requirement, and they are our laboratory when the universe will not cooperate. High-resolution cosmological runs can predict how CD halos grow, where profile breaks occur, and how intracluster light forms. They can also track the origin of stars, tagging whether they formed in place or were accreted from disrupted satellites. But simulations must be tested against data, not tuned to match it after the fact. The physics of feedback, stripping, and dynamical friction must reproduce multiple observables. If a model matches the brightness profile but fails to match kinematics or globular cluster distributions, it is not an explanation, it is a curve fit. This loops back to the black hole story, because the center can remember what the outskirts only imply. If IC1101's core is scoured, it could be a fossil of repeated supermassive black hole mergers. In that scenario, binary black holes eject stars from the center through gravitational slingshots, carving a low-density core that persists. A scoured core would support a merger-heavy history, and it would connect the galaxy's growth to gravitational wave events we have not yet heard. The core becomes a signature of past violence, while the halo becomes the debris field. Together, they would tell a coherent story. Repeated infill, repeated merging, and a cluster environment that never stops feeding the center. Future space-based gravitational wave observatories could detect massive black hole binaries, and those detections would be more than headlines. Such detections would timestamp the assembly of central giants. They would also test recoil kicks and merger rates in cluster centers, which determine whether black holes stay put or are displaced by asymmetric radiation. That would tell us whether IC 1101's nucleus grew by eating, merging, or both, and whether the cluster environment accelerates that growth. It would also connect a diffuse halo of starlight to a background hum of space-time ripples, linking the faintest photons to the deepest dynamics. NASA and international surveys are already pushing these frontiers, and the progress is incremental but relentless. New wide-field observatories will map low surface brightness structures with better control. The goal is not merely to see more, but to see more reliably, with calibration stable enough to trust the faintest gradients. Next-generation spectrographs will measure faint traces faster, turning sparse kinematics into full dynamical profiles. Instead of a handful of velocities, we'll build radial maps that show where the transition occurs. The difference between halo and intracluster light may reveal itself as a change in the very temperature of motion. New X-ray missions will refine cluster gas physics, measuring turbulence and feedback heating that break hydrostatic assumptions. If we can quantify non-thermal pressure support, we can correct mass estimates and better understand the depth of the cluster potential. That matters because the deeper the potential, the easier it is for diffuse stars to remain bound to the cluster rather than the galaxy. And new lensing surveys will expand the sample, which is the quiet revolution behind every record. Instead of one famous giant, we will compare many cluster centers with consistent methods. With statistics, we can ask whether IC 1101 is an outlier or a representative of a population we have undercounted. That comparison matters more than the record, because it changes what the record means. If IC 1101 is rare, it marks an extreme tale of cosmic assembly. If it is common, our census is incomplete, and our picture of galaxy growth has been systematically truncated at the faint end. Either outcome changes the story, and neither is comforting. Rarity implies special conditions and a violent history concentrated in a few nodes. Commonness implies we have been blind, and that the universe has been building enormous diffuse structures while our catalogues politely looked away. Now we confront the deepest possibility, the one that lingers after the data plots fade. There may be even larger galaxies or galaxy-like envelopes beyond current surveys, hiding in plain darkness. They would not announce themselves with bright cores, because their defining feature would be spread out light, not concentrated brilliance. They would be detected as subtle gradients, requiring patience, calibration, and skepticism in equal measure. The terrifying implication is simple. The universe may contain structures so extended that our catalogues cut them off by design, because our software and our definitions were optimized for brighter, cleaner objects. Yet the mystery does not weaken the chapter's conclusion, it sharpens it. Uncertainty is part of what IC 1101 teaches, and the lesson is methodological as much as cosmic. When we chase extremes, we also chase the edges of our own reliability. IC 1101 forces us to admit that edge is not a line, and never was. It is a fading probability, shaped by gravity, time, and the limits of detection. The galaxy does not stop. Our confidence does, and the stopping point depends on how carefully we subtract the sky. It also forces us to admit that our perspective is local, and our tools are built for convenience. We measure from inside one galaxy, with one atmosphere, using instruments built for bright targets. Even our language is local, because we grew up with objects that have borders, and the universe does not always share that preference. So the record is provisional, and it should be treated like a living claim. IC 1101 may stay number 1, or it may be demoted by a deeper survey and a stricter definition. Either way, the unsettling lesson remains, because the underlying physics does not care about our rankings. Gravity plus dark matter plus time can build structures so vast they erase human intuition, and they do it quietly, and the same processes that build them are indifferent to what lives inside them. The universe does not promise safe neighborhoods, even when it provides worlds. We return to the opening hook, now stripped of comfort, and we let it land with its full weight. If the Milky Way could fit inside a single galaxy, the real shock is that the boundary is negotiable. A galaxy can be so large that it becomes a region rather than an object, and that shift changes how we think. It becomes a gradient in a cluster, and the cluster becomes a node in a web, and the web becomes a map of forces we cannot see directly. That is the edge of knowledge. The farther we push, the more the universe refuses clean categories, and the more our maps become arguments. If IC 1101 is a record or a mirage, it still points to the same truth about cosmic architecture. IC 1101 became huge because it sits at Abell 2029's bottom, inside a deep, dark matter well. In X-ray maps, the cluster's hot gas glows like a stormy halo, and the galaxy lies near the calm eye. Over billions of years, galaxies fell inward, lost orbital energy through dynamical friction, and were cannibalized into a vast stellar envelope. Each pass stripped stars into long tidal streams, which then blurred into a diffuse glow that cameras barely separate from darkness. The same mergers fed a central supermassive black hole, delivering gas and stars toward an engine that once flared. Today the core can look quiet, yet its history is written in the cluster's heated plasma and in the galaxy's swollen profile. The boundary still blurs because the outer light blends into intracluster stars orbiting the cluster more than the galaxy. Astronomers argue about where galaxy ends because the physics changes gradually, not at a clean edge. That ambiguity is the point, because the cluster-scale halo is the true container. If IC 1101 is a record or a mirage, it still points to the same truth about cosmic architecture. The terrifying implication is not that the universe breaks rules, but that it follows them relentlessly. Given gravity, dark matter, and time, extremes are not rare accidents, they are natural endpoints. Hierarchical growth is the quiet algorithm of cosmology. Small structures merge into larger ones until the deepest wells dominate. Our intuition was trained on coastlines and lifetimes, not on cosmic wells and billion-year mergers. When we call something too big, we may be confessing a human scale, not a cosmic limit. IC 1101 is a visible crest on an invisible ocean, the cosmic web that shapes what we can see. Filaments feed nodes, nodes build clusters, clusters build central giants, and the light is only the afterimage. Even our history of discovery reflects that hidden scaffolding, because we learned galaxies were islands long before we inferred the dark matter holding them. Exoplanets remind us what is at stake, because worlds are common while safe histories are fragile. Earth is a thin atmosphere on a small rock, and the solar system is a local harbour. Voyager is a message in a bottle, drifting beyond familiar winds, and modern exploration, from new telescopes to SpaceX, is the next reach outward. In the final chapter, we decide what to do with that truth, and why the search continues anyway. The observable universe is not the whole universe, and our biggest galaxy may be only the biggest we can currently perceive. IC 1101 didn't appear as a neat, isolated object. It emerged as a case built from whispers of light, and from the physics that shapes them. We learned that largest is not a simple crown, because its outer glow dissolves into Abell 2029's intracluster light, where definitions, sky subtraction, and distance dimming decide what we can honestly claim. And we followed the real architect of that scale, time inside a deep dark matter potential, where mergers, tidal stripping, and dynamical friction turn a cluster core into a slow grinder, feeding a central giant and scattering the rest into a shared halo. That history has fingerprints, even if the crime scene is faint, and the evidence is still being collected in the dark. The core likely remembers early, violent major mergers, while the outer envelope hints at billions of years of smaller accretions, shredded satellites, and stars unmoored into streams that fade into a diffuse sea. The black hole at the centre may be both witness and weapon, growing through repeated meals and mergers, then regulating the cluster's cooling gas with outbursts that leave cavities, shocks, and heat where new stars should have formed. Abell 2029 itself became the frame that finally made sense of the monster, a gravitational city where hot X-ray gas outweighs starlight, where galaxies move at hundreds to thousands of kilometers per second, and where most of the mass is invisible. Dark matter was the missing weight that turned speculation into structure, the collisionless scaffold that builds filaments, nodes, and clusters long before the stars light up. It explains why IC 1101 can be so enormous without flying apart, because the galaxy is not the container. The cluster-scale halo is, and the edge is a handoff between two overlapping gravitational loyalties. That boundary problem is not a technical footnote, it is the heart of the terror, because it means nature doesn't always draw lines where our language demands them. Even our most familiar rulers, Earth, the outer planets, the Voyagers, collapsed into insignificance when placed against a halo that may stretch for millions of light years, and against a universe that hides its biggest structures in the faintest light. We also let the scale become personal by imagining worlds inside this architecture, and what a cluster environment might do to their chances in crowded cores. Radiation, stripping, and long ago black hole flares may have rewritten atmospheres, while the constant reshuffling of stars and gas reshapes the very idea of a stable cosmic neighbourhood. Yet the exoplanet revolution delivered a quieter counterpoint, because the universe is not only violent, it is also prolific, and it builds more worlds than our instincts can hold. The unease, then, is not just that IC1101 is huge, it's that